Tonight, we're going to explore something that will fundamentally change everything about our cosmic neighborhood. We're going to trace the future collision between our Milky Way galaxy and the Andromeda galaxy, an event that will reshape the entire structure of our corner of the universe over billions of years. This isn't science fiction or distant speculation. It's the inevitable result of gravity, time, and the measured motions of these two massive structures through space, confirmed by decades of painstaking astronomical observation. By the end of this journey, you'll understand not just what will happen when these galaxies meet, but what it means for Earth, our solar system, and the ultimate fate of everything we can see in the night sky. You'll grasp the timescales involved, timescales so vast they make all of human history seem like the briefest flicker of light. Before we dive in, if you enjoy these deep explorations of space and time, a quick like or subscribe would really help the channel grow. Now, let's begin our voyage into the far future. The cosmic dance begins. Look up at the night sky on a clear, moonless evening, far from the glow of city lights. That faint band of light stretching across the darkness is the Milky Way, our home galaxy. You're seeing it from the inside, looking through the disk of hundreds of billions of stars, gas clouds, and nebulae that make up this vast cosmic structure. It's a perspective unique to our position within it, a view that no observer outside the galaxy could ever experience. But there's something else visible on particularly dark nights, something that appears as just a smudge of light in the constellation Andromeda. That fuzzy patch, barely visible to the naked eye, is the Andromeda galaxy, cataloged by astronomers as Messier 31 or simply M31. It's the nearest large spiral galaxy to our own, and it's been an object of fascination for as long as humans have looked up at the stars. The first recorded observation of Andromeda came over 1,000 years ago. In the year 964, the Persian astronomer Abd al-Rahman al-Sufi described it in his Book of Fixed Stars, calling it a little cloud or nebulous smear. He combined the Greek constellation of Andromeda with the traditional Arabic constellation of two fish, and he noted this peculiar fuzzy patch at the fish's mouth. He had no idea what he was looking at. No one did for nearly another millennium. Though the object may have been known to astronomers before al-Sufi, his was the first written record that has survived to our time. Curiously, ancient Greek astronomers like Ptolemy mentioned several other nebulous objects, but never recorded Andromeda, despite it being easily visible to the naked eye. For a very long time after al-Sufi, observers simply noted its presence, this strange cloud-like object that didn't behave like a star. Right now, at this very moment, Andromeda sits approximately 2.5 million light years away from us. That's an almost incomprehensible distance. Light from Andromeda, traveling at 300,000 kilometers per second, or about 186,000 miles per second, the fastest speed possible in our universe, takes 2.5 million years to reach our eyes. When you look at Andromeda tonight, you're seeing it as it was when early humans on Earth were just beginning to use stone tools. Homo habilis walked the African savannas. Modern humans didn't exist yet. The entire span of recorded human history, all of civilization from the first cities to today, represents less than 1/4% of the time that light has been traveling from Andromeda to reach us. Think about that for a moment. The light entering your eyes right now left that galaxy before our species evolved. it traveled through the vast emptiness of intergalactic space for 2.5 million years, crossing distances so immense that our minds struggle to grasp them. And during all that time, during every second of that impossibly long journey, Andromeda has continued evolving, changing, forming new stars, and consuming old ones, completely unaware that someday, billions of years in the future, it will merge with the galaxy from which you're now observing it. But here's what makes this particularly fascinating. What transforms Andromeda from a distant object of curiosity into something directly relevant to our cosmic future. Andromeda isn't stationary in the sky. It's moving, and it's not moving away from us like most galaxies in the universe. It's coming toward us. Right now, Andromeda is approaching the Milky Way at approximately 110 kilometers per second, though some more recent measurements suggest the speed might be closer to 116 kilometers per second. That's about 250,000 to 260,000 miles per hour, or roughly 400,000 to 420,000 kilometers per hour. At that speed, you could circle Earth's equator in just over 6 minutes. It's faster than anything humans have ever built. It's a velocity that seems almost incomprehensibly rapid by any earthly standard. Yet despite this tremendous speed, the distance between our galaxies is so vast that this cosmic encounter will take billions of years to unfold. This is the profound strangeness of cosmic scales. Motion that seems impossibly fast by human standards becomes glacially slow when measured against the distances between galaxies. Andromeda had been approaching us for billions of years already, and it will continue approaching for billions more before the first close encounter occurs. Scientists have known for over a century that Andromeda was approaching us. In 1912, the American astronomer Vesto Slipher made a remarkable discovery using spectroscopy, the technique of splitting light into its component colors. When an object moves toward us, its light gets compressed slightly, shifted toward the blue end of the spectrum. When it moves away, the light stretches, shifting toward the red. This is called the Doppler effect, the same phenomenon that makes an ambulance siren change pitch as it passes you on the street. Slipher pointed his spectrograph at Andromeda and analyzed its light. What he found was unexpected. Most objects in the universe show a redshift, indicating they're moving away from us. This is how we know the universe is expanding. But Andromeda showed a blue shift. The galaxy was approaching at what Slipher measured as approximately 300 kilometers per second, making it one of the only large galaxies in the observable universe, moving toward us rather than away. For decades, this was just an interesting observation, a curious anomaly in a universe that seemed to be flying apart in all directions. Yes, Andromeda was moving toward us, but would it actually collide with the Milky Way? Or would it miss us, sailing past at some safe distance, like two ships passing in the night? The answer to that question required measuring something much more difficult than radial velocity, the component of motion directly toward or away from us. Scientists needed to measure Andromeda's tangential velocity, its sideways motion across the face of the sky. This is incredibly challenging because at Andromeda's distance, even a significant sideways velocity translates to an absolutely tiny angular motion. The galaxy appears to move across the sky at a rate measured in micro-arcseconds per year, angles so small they're almost impossible to detect even with our best telescopes. It took the Hubble Space Telescope, orbiting above Earth's atmosphere where observations aren't blurred by atmospheric turbulence, to finally answer this question definitively. Between 2002 and 2010, Hubble carried out a painstaking observation campaign. Astronomers carefully measured the positions of individual stars in Andromeda relative to hundreds of distant background galaxies, objects so far away they serve as fixed reference points. By comparing images taken years apart and averaging the measured positions of thousands of stars to reduce random errors, the team achieved measurements of unprecedented precision, accurate to tiny fractions of a pixel on the telescope's electronic detector. The results were published in 2012 by a team led by Roland van der Marel at the Space Telescope Science Institute and Sangmo Tony Sohn. They were definitive and somewhat startling. Andromeda's sideways motion was essentially zero, at least within the measurement uncertainties. The galaxy wasn't sailing past us at an angle. It was headed almost directly toward us, like a cosmic freight train barreling down the tracks. The team's conclusion was clear. Based on Hubble's measurements and computer simulations of the future trajectories of both galaxies, a collision between the Milky Way and Andromeda was virtually certain. The first close encounter would begin in approximately 375 to 4 billion years. The announcement made headlines around the world. Our galaxy's fate was sealed. We were on an unavoidable collision course with our largest neighbor, and nothing could prevent it. Gravity would see to that. But here's where the story takes an interesting turn, demonstrating how science constantly refines and sometimes revises our understanding. In 2025, a new study challenged this seeming certainty. A team led by astronomer Till Sawala at the University of Helsinki used the latest data from both the Hubble Space Telescope and the European Space Agency's Gaia spacecraft, which has been measuring the positions and motions of billions of stars in our galaxy with extraordinary precision, to create more sophisticated simulations than had been possible before. They did something previous studies hadn't fully accounted for. They included the gravitational effects of other nearby galaxies, particularly the Triangulum Galaxy, known to astronomers as M33, and the Large Magellanic Cloud, a satellite galaxy of the Milky Way that's large enough to exert a meaningful gravitational influence on the whole system. When you're trying to predict the behavior of gravitationally interacting objects over billions of years, even small additional forces can accumulate and significantly alter the outcomes. The team ran thousands of simulations using what's called Monte Carlo sampling. They took the current observational data on the positions, velocities, and masses of the galaxies, including the uncertainties in those measurements, and ran simulations with parameters randomly chosen from within those uncertainty ranges. Some simulations used the high end of the mass estimates. Others used the low end. Some used velocities at the upper limit of measurement uncertainty. Others used the lower limit. This approach allowed them to explore the full range of possible futures given our current knowledge. What they found surprised many scientists. When you account for these additional gravitational influences and the genuine uncertainties in our measurements, the picture becomes much less certain than the 2012 study suggested. According to their results, published in Nature Astronomy, there's approximately a 50% chance that the Milky Way and Andromeda will not undergo a full merger collision during the next 10 billion years. The galaxies might make a close pass, coming within 500,000 light-years of each other, gravitationally disturbing each other, but then swinging past and continuing on separate paths for a very long time. Or in some simulations, they might barely interact at all, their orbits keeping them apart more or less indefinitely. This uncertainty might seem frustrating, especially after the definitive sounding 2012 announcement, but it actually reveals something profound about the nature of scientific prediction and the limits of what we can know. Even with our most sophisticated telescopes and the most powerful computer simulations, predicting events billions of years in the future with absolute certainty remains beyond our reach. Small uncertainties in current measurements, tiny variations in the exact masses of galaxies, the influence of smaller neighboring galaxies, the distribution of dark matter that we can't directly observe. All of these factors compound over cosmic timescales, creating what's called chaotic behavior in the mathematical sense, where small changes in initial conditions can lead to dramatically different outcomes. Yet even with this uncertainty, most astronomers still consider a collision more likely than not. The best estimate, given all the data we have, suggests roughly even odds, may be tilted slightly toward collision. And if it happens, when it happens, if the universe follows that particular branch of possible futures, it will be one of the most spectacular events in the history of our local group of galaxies. So tonight, we're going to explore what that collision would look like, based on what we can infer from computer simulations and observations of other colliding galaxies throughout the universe. We'll examine what evidence suggests will happen to our solar system, what we can reasonably project about the ultimate fate of both galaxies, and what the far future might hold. We're going to take a journey through billions of years, watching as two massive spiral structures approach, collide, and potentially merge into something entirely new. Understanding our galactic neighbors. Before we can understand what happens when galaxies collide, we need to understand what galaxies actually are, how they're structured, and what they contain. Let's start with our own Milky Way. From our vantage point inside it, embedded in one of its spiral arms, about 2/3 of the way out from the center, the Milky Way appears as that familiar band of light stretching across the night sky on clear, dark evenings. But if we could somehow travel far outside our galaxy and look back, we'd see something magnificent. The Milky Way is what astronomers call a barred spiral galaxy. This means it has an elongated, bar-shaped structure at its center, composed of billions of densely packed stars, with graceful spiral arms extending outward from the ends of that bar. The galaxy measures approximately 100,000 light years in diameter, though some recent measurements of the outer disk suggest it might extend a bit farther, perhaps to 120,000 or even 150,000 light years, if you count the very faint outer regions. To cross from one edge to the other, even traveling at the speed of light, the fastest speed possible in our universe, would take 100,000 years or more. The galaxy contains somewhere between 100 billion and 400 billion stars. The uncertainty in this number reflects the difficulty of counting stars from inside the galaxy itself. We can't see all of them. Dust blocks our view in certain directions, particularly toward the galactic center, and the smallest, faintest stars, the red dwarfs that make up the majority of stellar populations, are difficult to detect individually, even in our own stellar neighborhood. So astronomers estimate the total count by measuring what they can see, modeling the galaxy's structure, and extrapolating. Each one of those stars is a sun, potentially with its own retinue of planets, moons, asteroids, and comets. Recent discoveries of exoplanets, planets orbiting other stars, suggest that planets are remarkably common. Nearly every star we examine closely appears to have at least one planet, and many have multiple planets. If this holds true across the galaxy, there could be hundreds of billions of planets in the Milky Way. Some fraction of those will be rocky worlds like Earth. Some will orbit in their star's habitable zone, the region where liquid water could exist on the surface. The number of potentially habitable worlds in just our galaxy alone might number in the billions. But visible matter, all those stars and gas clouds and dust, makes up only a small fraction of the Milky Way's total mass. Based on measurements of how fast stars orbit at various distances from the galactic center, astronomers have determined that the galaxy is embedded in a vast halo of dark matter, an invisible substance that we detect only through its gravitational effects. This dark matter halo extends far beyond the visible disk, reaching out perhaps 600,000 light-years or more from the galactic center. The nature of dark matter remains one of the deepest mysteries in physics. We don't know what it's made of. It doesn't emit light or absorb light or interact electromagnetically in any way we can detect. But it has mass, and therefore it has gravity. And that gravity is what holds galaxies together. Without dark matter, galaxies like the Milky Way would fly apart. The stars in the outer regions orbit too fast to be held by the gravity of visible matter alone. There must be additional mass, and lots of it distributed throughout and around the galaxy. The total mass of the Milky Way, including all its stars, gas, dust, and dark matter, comes to somewhere between 1 trillion and 1.5 trillion times the mass of our Sun. And of that total mass, based on what we can infer from rotation curves and other observations, roughly 85 to 90% is dark matter. Visible matter, everything we can see and touch and measure directly, makes up only about 10 to 15% of the galaxy's total mass. At the very center of the Milky Way sits a supermassive black hole that astronomers have named Sagittarius A star, often abbreviated as SGR-8A. This monster weighs approximately 4 million times the mass of the Sun, a figure determined by carefully tracking the orbits of stars near the galactic center. These stars move incredibly fast, completing their orbits in just a few years, despite being several light days or light weeks away from the black hole itself. By measuring their orbital periods and distances using basic Newtonian physics, the same laws that govern planetary orbits in our solar system, astronomers can calculate the mass of the object they're orbiting. SGR-A is not particularly active right now. It's not consuming large amounts of matter, not blazing brilliantly across the electromagnetic spectrum like the supermassive black holes at the centers of what we call active galaxies. It's relatively quiescent, occasionally flaring in X-rays when it swallows a small amount of gas, or when stars pass close enough to have material stripped away by tidal forces. But it's always there, warping space around it with its immense gravity, a dark heart at the center of our galactic home. Our solar system resides in a relatively quiet, boring neighborhood about 26,000 light-years from the galactic center. We're located in what's called the Orion Arm, or Orion Spur, a minor spiral arm that branches off from one of the major arms. We orbit the galactic center at approximately 220 kilometers per second, completing one full orbit every 225 to 250 million years. This is sometimes called a cosmic year or galactic year. The last time our solar system was in its current position relative to the galaxy's spiral arms, roughly 225 million years ago, dinosaurs had just begun to evolve on Earth. The supercontinent Pangaea was still intact. The next time we complete an orbit, assuming Earth still exists in any recognizable form, the planet will be transformed beyond anything we could imagine today. The continents will have drifted to new positions. New species will have evolved and old ones gone extinct. If humanity or any descendants of humanity still exist, they'll be so different from us that we might not even recognize them as related to our species. Now let's turn our attention to Andromeda, officially cataloged as Messier 31 or M31. Andromeda is the nearest large spiral galaxy to the Milky Way, and it's substantially bigger than our home. The galaxy measures approximately 220,000 light years in diameter, more than twice the size of the Milky Way, though some measurements of its faint outer regions suggest it might stretch even farther, perhaps to 250,000 light years or more in its outermost halo. It contains roughly 1 trillion stars, based on estimates from the galaxy's total luminosity and assumptions about the distribution of different stellar types. That's about 2 to 3 times the stellar population of our galaxy. If you could somehow start counting those stars at a rate of 1 per second and never stopped to eat or sleep or rest, you would need approximately 32,000 years to finish. That's longer than the entire span of human civilization from the first cities to today. Like the Milky Way, Andromeda is a barred spiral galaxy. It has a bright central bulge packed with old, yellowish-red stars, the product of star formation that occurred billions of years ago when the galaxy was young. Extending outward from this bulge are beautiful spiral arms filled with young blue stars and glowing pink emission nebulae, where new stars are currently being born from collapsing clouds of gas and dust. The galaxy is magnificent when viewed through large telescopes, one of the most studied and photographed objects in the night sky outside our own galaxy. At Andromeda's heart sits its own supermassive black hole, far more massive than Sagittarius A4. This black hole weighs somewhere between 100 million and 200 million times the mass of the Sun, with the best current estimates clustering around 140 million solar masses. That's roughly 35 times more massive than the Milky Way's central black hole. The difference is significant and tells us something about the different evolutionary histories of the two galaxies. A more massive central black hole suggests Andromeda has likely experienced more major mergers in its past, events that would have funneled gas into the galactic center and fed the black hole, allowing it to grow. For years, astronomers thought Andromeda might actually contain two supermassive black holes at its center, based on a peculiar double-peaked structure visible in high-resolution images of the galactic nucleus. This was a popular theory in the early 2000s, and many papers were published exploring the idea. But more recent observations and more sophisticated analysis, particularly from around 2020 onward, have largely ruled this out. What we now understand, based on the evidence available, is that what appears as two distinct regions is actually an eccentric disk of stars orbiting the single central black hole in an off-center elongated pattern. The black hole itself sits at one focus of this elliptical disk, creating an optical effect that mimics the appearance of two separate concentrations of light. It's a fascinating piece of galactic dynamics, but not evidence of a binary black hole system. Andromeda is massive. The total mass, including all its stars, gas, dust, and dark matter, comes to approximately 1.5 to 2 trillion times the mass of the Sun. There was a period around 2018 and 2019 when some studies suggested the Milky Way might actually be more massive than Andromeda, possibly weighing as much as 1.5 or even 2 trillion solar masses, which would make the two galaxies roughly equal in size. But subsequent analyses have generally walked back those claims. The current scientific consensus, based on the best data available, is that Andromeda remains the more massive of the two galaxies in our local group, though not by an enormous margin. We're more like siblings of slightly different sizes, rather than one being dramatically larger than the other. Andromeda, like the Milky Way, is surrounded by a retinue of smaller satellite galaxies that orbit it, held in place by its immense gravitational pull. At least 14 satellite galaxies have been identified orbiting Andromeda, with more likely remaining undiscovered in the faint outer regions where detection is difficult. These satellites range from dwarf spheroidal galaxies containing a few billion stars down to ultra-faint dwarfs with only a few thousand stars, barely more than large star clusters. The two largest and most famous are Messier 32 and Messier 110, both easily visible in the same telescopic field of view as Andromeda itself. M32 is a compact elliptical galaxy sitting dangerously close to its larger neighbor, only about 24,000 light-years from Andromeda's center. That's practically on top of the larger galaxy in cosmic terms. The tidal forces from Andromeda's gravity are slowly tearing M32 apart, stripping away its outer stars and pulling them into Andromeda's stellar halo. Stellar streams connect the two galaxies, visible in very deep photographic exposures as faint trails of stars stretching through space. Despite its small size, M32 harbors its own supermassive black hole at its center, weighing between 2 and 4 million solar masses. This is surprisingly large for such a small galaxy and suggests, based on what we know about the relationship between galaxy mass and central black hole mass, that M32 might once have been much larger. It may have been a more substantial galaxy that lost most of its stars during close encounters with Andromeda, leaving behind only the dense central core with its unusually massive black hole. This is one possible explanation, though there are others, and the true history of M32 remains a topic of active research. M110, also cataloged as NGC 205, is larger but orbits farther out at about 170,000 light-years from Andromeda's center. It's a dwarf spheroidal galaxy, elongated in shape and containing several billion stars. Like M32, it's being disrupted by Andromeda's tidal forces. Stellar streams connect M110 to Andromeda, visible in deep photographs as faint trails of stars stretching across space, evidence of the ongoing process of galactic cannibalism. These streams represent stars that have been pulled away from the dwarf galaxy and now follow similar orbits around Andromeda. Eventually, all of M110's stars will join Andromeda's halo, scattered and mixed with the larger galaxy's stellar population. The other satellites are smaller and fainter, many of them ultra-faint dwarf galaxies, discovered only in recent decades using sensitive digital cameras on large telescopes. These tiny galaxies contain only thousands to hundreds of thousands of stars, making them incredibly difficult to detect against the background sky. They're often dominated by dark matter, with dark matter outweighing visible matter by factors of hundreds or even thousands. to 1, making them valuable laboratories for studying dark matter's properties and distribution. One intriguing feature of Andromeda's satellite system has puzzled astronomers for years. Many of the satellites orbit in a thin plane, rather than being randomly distributed in all directions around the galaxy. This planar structure was initially considered puzzling because computer simulations of galaxy formation in a universe dominated by dark matter generally predict that satellite galaxies should be distributed more spherically. The planar arrangement was even suggested by some researchers as potential evidence challenging the standard model of cosmology. However, more recent thinking, particularly over the past few years as more sophisticated simulations have been run, has converged on a likely explanation. The satellites probably formed from a single major merger event between 8 and 10 billion years ago, when a large galaxy collided with Andromeda. The collision tore apart the incoming galaxy, and its debris formed the current generation of satellite galaxies. Because these tidal dwarf galaxies all formed from the debris of one collision, they would naturally lie in a plane defined by the orbit of the original intruder. This explanation fits well with other evidence that Andromeda experienced a major merger in its past, evidence we can see in the disturbed structure of Andromeda's stellar disk and halo. Both the Milky Way and Andromeda are part of what astronomers call the local group, a collection of more than 80 galaxies bound together by gravity. The local group spans approximately 10 million light years in diameter, and it's dominated by 3 large galaxies: Andromeda, the Milky Way, and the Triangulum galaxy, also called M33. Triangulum is the third largest member, containing perhaps 40 billion stars, substantially smaller than either Andromeda or the Milky Way, but still a significant spiral galaxy in its own right. The rest of the local group consists of smaller satellite galaxies, dwarf galaxies, and irregular galaxies. These include the Large and Small Magellanic Clouds, 2 irregular galaxies visible from the southern hemisphere that orbit the Milky Way. The Large Magellanic Cloud is the 4th largest member of the local group, containing perhaps 30 billion stars. All these galaxies are gravitationally bound together, a small island of structure in an expanding universe. On the largest scales, the local group is part of the Virgo supercluster, a much larger structure containing thousands of galaxies. And the Virgo supercluster is itself part of an even larger structure called Laniakea, a gravitationally bound system of superclusters containing 100,000 galaxies or more. These are the largest structures in the known universe, vast cosmic webs of galaxies separated by immense voids of nearly empty space. But our focus tonight is on the much more local drama playing out between just 2 galaxies, the Milky Way and Andromeda. These are our cosmic neighbors, the galaxies that will determine the fate of our local group over the next 10 billion years. The discovery of the collision course, the realization that the Milky Way and Andromeda are on a collision course, didn't come suddenly. It emerged gradually over the course of the 20th century as astronomers developed better tools for measuring the distances and motions of galaxies. The story really begins in the early 1920s with Edwin Hubble's groundbreaking observations. Before Hubble, the nature of these spiral nebulae was hotly debated. Some astronomers thought they were clouds of gas within our own Milky Way. Others suspected they might be distant galaxies, separate island universes far beyond our own. The debate reached its peak in 1920 with what's now called the Great Debate between astronomers Harlow Shapley and Heber Curtis. Hubble settled the question in 1923 and 1924. Using the 100-inch telescope at Mount Wilson Observatory in California, the largest telescope in the world at that time, he was able to resolve individual stars in the Andromeda Nebula, as it was then called. More importantly, he identified a special type of star called a Cepheid variable. Cepheid variables are massive stars that pulsate regularly, brightening and dimming with periods ranging from days to months. In 1912, astronomer Henrietta Swan Leavitt had discovered that the pulsation period of a Cepheid is directly related to its true brightness, its intrinsic luminosity. Measure the period, and you know how bright the star truly is. Compare that to how bright it appears from Earth, and you can calculate its distance. It's an elegant method that revolutionized astronomy. Hubble measured several Cepheids in Andromeda. His initial distance estimate was about 900,000 light-years, which we now know was too small because he didn't realize there are actually two types of Cepheids with different period luminosity relationships. But it was close enough to prove decisively that Andromeda was far beyond the boundaries of the Milky Way. It was a separate galaxy, an island universe in its own right. The announcement fundamentally changed our understanding of the cosmos. The universe was far larger than anyone had imagined. As we mentioned earlier, Vesto Slipher had already measured in 1912 that Andromeda was approaching us based on the blue shift of its light. This was known, but for decades, no one knew whether Andromeda would actually collide with us or pass by at a safe distance. The missing piece was Andromeda's tangential velocity, its sideways motion across the sky. This measurement requires incredible precision. At Andromeda's distance, even a significant velocity translates to a barely perceptible motion across the sky. From Earth, Andromeda moves across the celestial sphere at roughly 65 micro-arcseconds per year. A micro-arcsecond is 1/millionth of an arcsecond, which is itself 1/3600th of a degree. To put that in perspective, it's roughly the angular size of a penny viewed from 10,000 miles away. Measuring such tiny motions requires long-time baselines and extremely precise instruments. The Hubble Space Telescope provided both. Between 2002 and 2010, a team led by Roland van der Marel and Sangmo Tony Sohn carried out a painstaking observation campaign specifically designed to measure Andromeda's tangential motion. They used Hubble's advanced camera for surveys to take high-resolution images of fields in Andromeda, capturing thousands of individual stars. Then they waited several years and took new images of the exact same fields. By comparing the positions of stars in Andromeda against hundreds of distant background galaxies, which serve as fixed reference points because they're so far away they show no measurable motion over timescales of years or even decades, the team could detect tiny shifts in the positions of Andromeda's stars. They repeated this process for many different fields scattered across Andromeda's disk. By averaging the measurements from thousands of stars, they could reduce random errors and achieve unprecedented precision. The results were published in 2012 in the Astrophysical Journal. The team found that Andromeda's sideways motion was essentially zero, or more precisely, small enough that it fell within the measurement uncertainties. This meant Andromeda wasn't sailing past us at an angle. It was headed almost directly toward us. Given the measured approach, velocity, and distance, A collision was all but certain. The team ran computer simulations to project the future trajectories of both galaxies. They accounted for the gravitational attraction between them, which grows stronger as they approach. They included the effects of dark matter halos, which extend far beyond the visible disks and dominate the gravitational interactions. The simulations showed a clear pattern. The galaxies would approach each other over the next few billion years, make a first close pass in about 3.75 billion years, then separate again before falling back together for subsequent encounters. The announcement made international headlines. Major news organizations around the world reported that our galaxy was doomed to collide with Andromeda. Some articles were more sensationalistic than others, but the core message was accurate. The Milky Way and Andromeda are on a collision course, and absent some extremely unlikely intervention, they will merge in the relatively distant future. But as we've discussed, the 2025 study by Til Sawala and colleagues added important nuance to this picture by including the gravitational effects of other nearby galaxies and properly accounting for all the measurement uncertainties. They showed that the collision is less certain than the 2012 study suggested. There's roughly a 50% chance it won't happen, at least not in the next 10 billion years. This doesn't mean the 2012 study was wrong. It means that as we gather more data and refine our measurements, and as we include more complexity in our models, the picture can shift. This is how science works. It's not about absolute certainty, but about developing the best possible understanding, given current evidence, always ready to update that understanding as new evidence becomes available. The question of whether the collision will happen remains open, but the possibility is real enough, and the implications are profound enough that it's worth exploring in detail what would happen if it does occur. And that's what we'll do for the rest of this journey. Measuring the cosmos, the distance ladder. Understanding the Milky Way, Andromeda collision requires understanding how we measure these vast cosmic distances. How do we actually know Andromeda is 2.5 million light years away? How can we be confident in our measurements of galaxies so distant that the light we see left them before humans evolved? The answer lies in one of astronomy's most ingenious achievements, the cosmic distance ladder. It's called a ladder because it's a series of methods that build on each other, each step reaching farther into space, each depending on the rungs below it being accurate. The foundation starts right here in our solar system. We can measure distances to nearby objects, like the moon using radar. Send a radio pulse, time how long it takes to bounce back, calculate the distance. This gives us the Earth-Moon distance with extraordinary precision, accurate to within a few centimeters. For planets and asteroids, we use similar techniques or observe them from multiple positions on Earth, using parallax, the apparent shift in position when viewed from different angles. These methods give us the astronomical unit, Earth's average distance from the Sun, at about 150 million kilometers, or 93 million miles. This becomes our baseline for measuring everything beyond the solar system. For nearby stars, parallax still works, but now we're using Earth's orbit as our baseline. As Earth moves around the Sun over the course of a year, nearby stars appear to shift position slightly against the background of more distant stars. The closer the star, the larger the shift. By measuring this angular shift and knowing the size of Earth's orbit, we can calculate the star's distance using basic trigonometry. The Hipparcos satellite in the 1990s and the Gaia spacecraft, currently in operation, have measured parallaxes for billions of stars in our galaxy with unprecedented precision. But parallax only works out to a few thousand light years at most. Beyond that, the shifts become too small to measure accurately, even with our best instruments. We need a different technique. That's where standard candles enter the picture. A standard candle is an object whose true brightness we know. By measuring how bright it appears from Earth, we can calculate how far away it must be using the inverse square law of light. It's like seeing a light bulb and, knowing it's a 100-watt bulb, figuring out how far away it is based on how dim it looks. The most important standard candle for measuring distances to nearby galaxies is the Cepheid variable star. Cepheids are massive, evolved stars that pulsate regularly, growing brighter and dimmer with periods ranging from days to months. The crucial discovery made by Henrietta Swan Leavitt in 1912 while working at Harvard College Observatory is that a Cepheid's pulsation period is directly related to its true luminosity. Longer period means brighter star. It's a tight, well-defined relationship. Measure a Cepheid's pulsation period by watching how its brightness changes over time, and you know its true luminosity. Compare that to how bright it appears from Earth, and you can calculate its distance. It's an elegant method that revolutionized our understanding of the universe's scale. Edwin Hubble used this technique in the 1920s to measure Andromeda's distance. Using the 100-inch telescope at Mount Wilson Observatory, he identified multiple Cepheid variables in Andromeda. His initial estimate was about 900,000 light years, which was too small because he didn't yet know there are two types of Cepheids with different period luminosity relationships. But it was close enough to prove decisively that Andromeda was far beyond the Milky Way. Modern measurements using the Hubble Space Telescope and improved calibrations of the Cepheid distance scale have refined the distance to 2.5 million light years with uncertainties of only a few percent. This is remarkably precise for measuring across intergalactic space. For galaxies too distant to resolve individual Cepheids, we use even brighter standard candles. Type Ia supernovae, exploding white dwarf stars, are so luminous they can be seen billions of light years away. These explosions have remarkably consistent peak brightnesses, making them excellent distance indicators. By calibrating the Type Ia supernova scale using galaxies where we know the distance from Cepheids, we can measure distances across cosmological scales. This technique helped discover that the universe's expansion is accelerating, a discovery that earned the Nobel Prize in 2011. The cosmic distance ladder is fragile, in one sense. If the lower rungs are wrong, everything above becomes uncertain. But it's also robust because we can check it in multiple ways. We can measure some galaxies using both Cepheids and supernovae and verify the methods give consistent results. We can compare distance measurements from entirely independent techniques. The fact that everything fits together into a coherent picture gives us confidence we understand the cosmic distance scale. Andromeda sits on a crucial rung of this ladder. It's close enough to measure accurately using Cepheids, yet far enough to represent extragalactic distances. Understanding Andromeda's distance helps us calibrate methods for measuring much more distant galaxies. It's a bridge between our local cosmic neighborhood and the broader universe beyond. When Andromeda hits the Milky Way, Part 2, The timeline. When will it happen? The question everyone asks when they first hear about this collision is simple. When? When will it happen? When should we expect the first encounter? When will the final merger complete? The answers depend on which study you look at and what assumptions are built into the simulations, but we can sketch out a general timeline based on the best current evidence. Let's start with what we know most confidently. Andromeda is currently approaching us at approximately 110 to 116 kilometers per second. That velocity has been measured repeatedly using spectroscopy and is well established. The distance is also well known, 2.5 million light years, measured using Cepheid variable stars and other standard candles. These are solid, reliable measurements. Where uncertainty creeps in is when we try to project these motions forward billions of years into the future. We need to account for the gravitational attraction between the galaxies, which increases as they approach. We need to model the distribution of dark matter in both galaxies' halos, which dominates the gravitational field but can't be directly observed. We need to consider the influence of other nearby galaxies. And we need to account for the fact that galaxies aren't point masses, but extended objects that will gravitationally interact in complex ways as they approach. Different research teams have tackled this problem using computer simulations, and they've arrived at somewhat different timelines, though the overall picture is remarkably consistent. The 2012 study by van der Merel and colleagues, using Hubble's measurements of Andromeda's motion, predicted the first close encounter would occur in approximately 3.75 billion years from now. Their simulations showed the galaxies making a first pass, then separating, then falling back together for subsequent encounters over the next few billion years. The final merger, when the two galactic cores would combine into a single structure, would be complete roughly 5 to 7 billion years from now. A more detailed study published in 2020 in the journal Astronomy and Astrophysics by Riccardo Schiavi and colleagues at Sapienza University of Rome provided additional precision. This team used direct n-body simulations, a computational technique that models the gravitational interactions between many individual particles, each representing a cluster of stars or dark matter. Their simulations included not just the two galaxies, but also the diffuse gas and material between them, which can create drag and affect the trajectories. According to Schiavi's team, the first close approach will occur in approximately 4.3 billion years, slightly later than the 2012 estimate. The galaxies will then separate and fall back together multiple times over an extended period. The full merger, when the two galaxies have completely combined into a single structure, will take approximately 10 billion years from now to complete. This is notably longer than some earlier estimates, and the difference appears to stem from including the effects of the intergalactic medium and using more sophisticated modeling of the dark matter halos. Other studies have given different numbers. Some suggest the first encounter might occur as soon as 3.5 billion years from now. Others push it out to 4.5 or even 5 billion years. The final merger timescale also varies, with estimates ranging from 6 billion to 10 billion years from the present. These variations aren't contradictions. They reflect genuine uncertainties in our knowledge and differences in modeling approaches. We don't know the exact mass of either galaxy with perfect precision. We don't know the exact distribution of dark matter in their halos. We don't know precisely how much gas exists in the space between the galaxies. Small variations in any of these parameters can shift the timeline by hundreds of millions or even billions of years. The 2025 study by Sawala added another layer of complexity by showing that when you include other nearby galaxies and properly account for all measurement uncertainties, there's roughly a 50% chance the collision might not happen at all within the next 10 billion years, or at least might not result in a full merger. The galaxies might make close passes, but remain distinct structures for much longer than previously thought. So, what can we say with confidence? Based on the weight of evidence from multiple independent studies, if the collision occurs, the most likely timeline appears to be first close encounter, somewhere between 3.5 and 4.5 billion years from now, with 4 billion years being a reasonable central estimate. Complete merger, somewhere between 6 and 10 billion years from now, with estimates clustering around 7 to 8 billion years based on more recent, sophisticated simulations. But these numbers come with substantial error bars, uncertainties that reflect the genuine limits of our ability to predict events so far in the future. What we can say is that the collision, if it happens, will begin sometime in the next 4 to 5 billion years, and will take several billion years to complete once it starts. To put these timescales in perspective, consider that Earth is approximately 4.5 billion years old. The first close encounter will occur roughly as far in the future as Earth's entire history extends into the past. Everything that has happened on this planet, from its formation to the emergence of life to the evolution of humans to the present day, all of that spans the same amount of time as we have left before the galaxies begin their dance, and the collision will last for a period comparable to Earth's entire existence. From the first encounter to the final merger will take 3 to 6 billion years, a time span during which, if Earth's history is any guide, entire new forms of life could evolve from simple beginnings to civilization and beyond. These are timescales that dwarf human comprehension. All of recorded human history, from the first cities in Mesopotamia to today, spans perhaps 6,000 years. The entire existence of our species, Homo sapiens, spans roughly 300,000 years. The collision will unfold over timescales tens of thousands or even millions of times longer than the entire existence of humanity. The first encounter. Let's imagine we could somehow fast forward through those billions of years and watch the first close encounter unfold. What would it look like? What would happen during that first cosmic collision? Based on computer simulations and observations of other colliding galaxies in the universe, we can paint a reasonably detailed picture, though we should remember that the details depend on many factors that are difficult to predict precisely. As the galaxies approach over billions of years, Andromeda will grow larger in Earth's sky, assuming Earth still exists in any recognizable form. Currently, Andromeda appears as a small, faint smudge visible to the naked eye under dark skies, but as it draws nearer, it will gradually expand, becoming more prominent, eventually rivaling the Moon in apparent size. About a billion years before the first encounter, Andromeda would span several degrees across the sky, far larger than its current appearance, but still relatively faint because its light is spread over a larger area. The individual spiral arms might become visible to the naked eye under dark skies. Bright star-forming regions and giant star clusters in Andromeda would appear as distinct points of light. By a few 100 million years before the encounter, Andromeda would dominate a large portion of the sky, The spiral structure would be obvious, a vast cosmic pinwheel spanning tens of degrees. The view would be spectacular, though at this point, assuming any form of life on Earth survived to witness it, observers would know that dramatic changes were coming. During the actual first close approach, several things would happen more or less simultaneously. The gravitational fields of the two galaxies would begin to seriously influence each other. Tidal forces, differences in gravitational pull between the near and far sides of each galaxy, would start to distort the orderly spiral structures. Stars in the outer regions of both galaxies would feel these tidal forces most strongly. Some would be pulled outward, away from their home galaxy, forming long streamers of stars extending into intergalactic space. These are called tidal tails, and we've observed them in many colliding galaxy pairs throughout the universe. The tails can extend for hundreds of thousands of light years, rivers of stars pulled from the galaxies by gravitational forces. But here's something crucial to understand. When galaxies collide, the stars themselves almost never collide with each other. Space is mostly empty, and stars are separated by vast distances. In our region of the Milky Way, the nearest star to the Sun is Proxima Centauri at 4.2 light years away. Even in the dense cores of galaxies where stars are more closely packed, the average distance between them is still measured in light months or light years. When two galactic disks pass through each other, the stars from each galaxy simply thread between the stars of the other galaxy, like two swarms of gnats passing through each other. The probability of any two stars actually colliding is negligible, far less than 1 in a trillion. This is one of the remarkable features of galaxy collisions. Despite the name collision, almost nothing actually hits anything else on a stellar scale. What does collide violently and dramatically is the gas. Both the Milky Way and Andromeda contain vast amounts of interstellar gas, primarily hydrogen in atomic and molecular form. This gas exists in clouds ranging from small dense cores to enormous diffuse regions spanning hundreds of light years. When the two galactic disks interpenetrate, these gas clouds slam into each other. Gas collisions are fundamentally different from stellar interactions. When two gas clouds collide, they don't pass through each other. They compress, heat up, and create shock waves. The compression can trigger gravitational collapse in the densest regions, causing the gas to fragment and form new stars. This is called a starburst, a period of intense, rapid star formation. Computer simulations suggest that during the first close encounter between the Milky Way and Andromeda, the rate of star formation in both galaxies could increase dramatically, perhaps by a factor of 10 or more compared to current rates. Millions of new stars might form in a relatively short period, measured in tens or hundreds of millions of years rather than billions. These newly formed stars would be disproportionately massive. When gas collapses rapidly under compression from a collision, it tends to form more high-mass stars than normal slower star formation. Massive stars are spectacularly luminous, shining thousands or even millions of times brighter than the sun. They also live fast and die young, exploding as supernovae after only a few million years. The result would be a spectacular light show, visible across millions of light years. The colliding regions would blaze with the blue light of young, hot, massive stars. Pink and red emission nebulae would glow as ultraviolet radiation from the hot stars ionizes surrounding hydrogen gas, and supernovae would flash across the merged structure every few years on average, each one briefly outshining billions of normal stars. From a vantage point outside the two galaxies, the sight would be breathtaking. Two massive spiral structures interpenetrating, their disks warped and distorted, long tidal tails streaming away into space, and the whole system blazing with newly formed stars and the explosive deaths of massive stars. It would be one of the most beautiful and dramatic sights in the universe. The first encounter wouldn't last long by cosmic standards. The galaxies would pass through each other over a period of perhaps a few 100 million years. Then they would separate, moving apart as their velocities carry them past each other. But they wouldn't escape. Gravity would slow them down, stop them, and pull them back together. The simulations show that after the first pass, the galaxies would separate to perhaps 500,000 light years or so, then begin falling back together for a second encounter. During the period of separation, both galaxies would be dramatically changed from their original spiral forms. The orderly disk structures would be warped, tilted, and disturbed. Tidal tails would extend in multiple directions. Stars would be on chaotic orbits, rather than the relatively organized rotation of an undisturbed spiral. The galaxies would look messy, asymmetric, irregular. This is exactly what we observe when we look at galaxies caught in the act of colliding elsewhere in the universe. They appear chaotic and disturbed, with structures that don't fit neatly into the standard classification scheme of spirals and ellipticals. They're galaxies in transition, caught between their past as orderly spirals and their future as merged systems. Multiple passes, a billion-year ballet. The collision between the Milky Way and Andromeda isn't a single event. It's a process, a dance that plays out through multiple encounters over billions of years. Understanding why this takes so long requires understanding orbital dynamics and how energy is dissipated in galaxy mergers. When two massive objects orbit each other, their paths are determined by their mutual gravitational attraction and their velocities. If one object is much more massive than the other, like the Sun and Earth, the smaller object orbits in a relatively simple ellipse. But when the two objects have comparable masses, like the Milky Way and Andromeda, things become more complex. They orbit around their common center of mass, which lies somewhere in the space between them, and their paths can be quite complicated. During the first close pass, enormous amounts of energy and angular momentum are exchanged through gravitational interactions. Stars on the outer edges of both galaxies are accelerated by close encounters with stars from the other galaxy. Some stars gain energy and are flung into higher orbits or even ejected entirely. Others lose energy and sink toward the galactic centers. This energy exchange is crucial. It's the mechanism by which the orbital energy of the galaxies themselves gets transferred to individual stars. As stars get scattered to higher orbits or ejected, they carry away energy, leaving the galactic cores with less orbital energy. This causes the cores to spiral closer together. The process is called dynamical friction, and it's fundamental to understanding how galaxies merge. Imagine a massive object moving through a sea of smaller objects, like a bowling ball rolling through a field of marbles. As it passes, it gravitationally attracts the smaller objects, pulling them along. But by Newton's third law, the smaller objects pull back on the massive object, slowing it down. Over time, This friction causes the massive object to lose energy and sink toward the center of the system. During galaxy mergers, the galactic cores act like those bowling balls, and the surrounding stars act like marbles. With each pass, more stars get scattered, carrying away more energy, causing the cores to sink closer together. After the first pass, the galaxies separate, but they don't escape each other. Their velocities have been reduced by the energy transferred to ejected stars and by tidal interactions. According to the simulations, they stop at a distance of perhaps 500,000 light years, and begin falling back together. The timescale for this depends on the specifics of the first encounter, but it typically takes a few 100 million to perhaps 1 billion years. The second encounter is often more violent than the first. The galaxies have less angular momentum now, having lost some during the first pass, so they can approach more directly. The collision is more head-on. More stars are scattered. More gas clouds collide, potentially triggering another burst of star formation, though the intensity might be lower because some of the gas was already consumed during the first starburst. The tidal forces during the second pass are often stronger because the galaxies can penetrate more deeply into each other's structures. This creates even longer streamers and tails of stars stretching across space, visible patterns that we've observed in many colliding galaxy systems throughout the universe. Computer simulations show that it typically takes 3, 4, or sometimes 5 passes before two comparable galaxies fully merge. Each pass removes more orbital energy through tidal interactions and dynamical friction. Each pass causes the central regions to sink closer together. Eventually, there's insufficient orbital energy remaining for the cores to separate again. They merge, and the two galaxies become one. Between the close encounters, during the periods when the galaxies are separated, they would present an increasingly chaotic appearance. Tidal streams would crisscross the space between them, stars from both galaxies scattered across hundreds of thousands of light years. The orderly spiral structures would be completely disrupted, replaced by amorphous clouds of stars with no clear pattern. This chaotic phase can last for billions of years, according to the simulations. The galaxies are still distinct structures in some sense, still recognizable as two separate concentrations of stars, but they're gravitationally locked together, orbiting their common center of mass, slowly spiraling inward with each pass. An observer watching from a safe distance would see what looks like two elliptical or irregular galaxies orbiting each other, shedding long tidal tails with each close approach, gradually drawing closer together over timescales measured in billions of years. It would be a slow-motion cosmic ballet, graceful in its own way, despite the violence of the forces involved. During each pass, the star formation rate would likely spike as gas clouds collide, though the effect might diminish with subsequent passes as the available gas gets depleted. Observations of colliding galaxies elsewhere in the universe show that star formation can be increased by factors of 10 or even 100 during the active phase of a merger. The classic example is the antennae galaxies, which we'll discuss in detail later. These galaxies are in the middle of their merger, and their collision has triggered the formation of thousands of massive star clusters, visible in Hubble Space Telescope images. However, it's worth noting that by the time the Milky Way and Andromeda collide, both galaxies will have exhausted much of their gas. star formation in both galaxies is gradually declining. We're converting our gas into stars, and eventually we'll run out. In another few billion years, the Milky Way will have substantially less gas available than it does today. Andromeda is in a similar situation. This suggests that the starburst during the collision might be less intense than it would be if the galaxies collided today. There will still be gas, and there will still be star formation triggered by the collision, but it might not be the spectacular fireworks show we see in some colliding galaxy pairs that are gas-rich. It could be more subdued, though still far more active than the current quiet star formation in either galaxy. Finally, after multiple encounters spanning perhaps 3 to 6 billion years from the first pass to the final merger, the cores combine. The two central bulges, each containing hundreds of billions of stars, merge into a single massive structure. The two supermassive black holes at the centers of the galaxies, which have been orbiting each other at progressively smaller radii, finally come close enough to merge themselves. By this point, the combined system no longer resembles two separate galaxies. It has become a single giant elliptical galaxy, the spiral arms long since destroyed by tidal interactions, the disk structures disrupted, stars, now on orbits, taking them in all directions rather than rotating in a single plane. What emerges is fundamentally different from either parent galaxy, a structure shaped by violence, rather than the gradual accumulation of gas and stars over billions of years of quiet evolution. The black hole merger. At the heart of every large galaxy sits a supermassive black hole. The Milky Way's black hole, Sagittarius A star, weighs about 4 million solar masses. Andromeda's central black hole weighs between 100 and 200 million solar masses, roughly 35 times more massive. When the galaxies merge, their black holes will merge too, but this process is neither simple nor immediate. It will take millions of years to unfold once the galaxies themselves have combined. After the galactic disks merge and the two cores combine, the black holes are initially separated by tens of thousands of light years. They're each embedded in their own dense stellar cusp, a concentration of stars orbiting very close to the black hole. As the merger progresses, these cusps sink toward the center of the merged galaxy through the same dynamical friction process that brought the galactic cores together. Dynamical friction works efficiently when there are lots of stars around. As each black hole and its surrounding stellar cusp moves through the sea of stars in the merged galaxy, it gravitationally attracts them, pulling them along. They pull back, extracting orbital energy from the black hole system and causing it to sink inward. According to Chiavi's 2020 study, this process takes millions to tens of millions of years. Over this period, the two black holes spiral inward until they're separated by only a few light years. At this point, they're close enough to form a gravitational binary system. They begin orbiting each other, their paths determined by their mutual gravitational attraction, just like binary stars orbit their common center of mass. But they're still not close enough to merge. They need to lose more orbital energy to spiral together. And here's where things get interesting. Dynamical friction becomes less effective at this stage because there aren't as many stars in the immediate vicinity of the binary. The black holes have already scattered or ejected most of the nearby stars through gravitational interactions. This is sometimes called the final parsec problem in the technical literature. A parsec is about 3.26 light years, And the question is, how do supermassive black holes get from a few light years apart to actually merging? For years, this was genuinely puzzling to astronomers. The solution, based on what simulations now suggest, involves several mechanisms working together. First, if there's gas around the binary, the black holes can interact with it. Gas falling toward the binary loses energy through friction and viscosity, and this can carry orbital energy away from the black hole pair, causing them to spiral closer. Second, the binary can scatter individual stars that pass nearby on highly elliptical orbits. Each scattering event extracts a small bit of orbital energy from the binary, gradually shrinking the orbit. This is inefficient because stars on the right kind of orbits to scatter effectively become rare once the binary has ejected most of the nearby population. But over millions of years, enough scattering events can occur to make a difference. Third, if the merged galaxy is rotating or has a triaxial shape, rather than being perfectly spherical, the black holes can interact with the overall gravitational potential of the galaxy itself, exchanging energy with the large-scale distribution of matter. Computer simulations by Schiavi and colleagues specifically modeled this process for the Milky Way Andromeda merger. They found that after the galaxies merge into a single structure, the two black holes will form a bound binary and then spiral together over a timescale of approximately 16.6 million years. Other studies give similar timescales, typically between 10 and 20 million years, for the black holes to go from forming a binary to actually merging. This might sound like a long time, and by human standards it is, but in the context of galaxy evolution, it's incredibly brief. The galaxies take billions of years to merge. The black holes, once they form a binary, merge in just tens of millions of years, less than 1% of the total merger timescale. As the black holes spiral inward, they begin emitting gravitational waves. Gravitational waves are ripples in spacetime itself, predicted by Einstein's general theory of relativity in 1915, and first directly detected by the LIGO Observatory in 2015. When massive objects accelerate, particularly when they orbit each other, they create disturbances in the fabric of spacetime that propagate outward at the speed of light. For most of their in spiral, while the black holes are still relatively far apart, the gravitational waves are too weak to have much effect. But as the separation decreases, the wave emission increases dramatically. The power radiated in gravitational waves scales with extremely high powers of the orbital frequency. When the black holes get close, the emission becomes enormous. According to Schiavi's calculations, just before the merger, the gravitational wave luminosity reaches approximately 10 to the power of 19 solar luminosities. Let me emphasize what that means. That's 10 quintillion times the power output of the sun. It's more energy than all the stars in the entire observable universe emit as electromagnetic radiation, as light, during the same period. The merging black holes briefly outshine the entire universe, not in light, but in gravitational waves. The waves carry away energy and angular momentum from the binary, causing the black holes to spiral together even faster in a runaway process. When they're within about 1 light year of each other, the gravitational wave emission becomes the dominant mechanism removing energy from the system. By the time they're within a light month, they're radiating as much energy as 1,000 suns. At a light week, 1,000,000 suns. At a light day, 1 billion suns. The numbers become almost absurd. The final plunge takes only seconds. The two black holes, each between about 4 million and 200 million times the mass of the Sun, spiral together in a final death dance. They're moving at significant fractions of the speed of light, orbiting each other potentially hundreds or thousands of times per second in those final moments. The space-time around them is churning, warping, forming a maelstrom of gravitational energy. And then they merge, the two event horizons, the surfaces beyond which nothing can escape, touch and combine. For a brief moment, the merged black hole is wildly asymmetric, violently distorted from the spherical shape that a non-rotating black hole would have. It oscillates, radiating away the asymmetry as gravitational waves, ringing like a struck bell, but in space-time rather than in material. Within a few more seconds, it settles into a stable configuration. The final merged black hole will weigh approximately 100 to 200 million solar masses, depending on the exact masses of the original black holes. A small fraction of the total mass, perhaps a few percent, will have been radiated away as gravitational wave energy during the inspiral and merger. This might sound small, but it represents an enormous, absolute amount of energy, equivalent to the mass energy of millions of suns completely converted to pure radiation. Could this merger be detected? Not from Earth in our current era. We're too close in time, and the technology doesn't exist yet. But Schiavi's team calculated that if a similar merger occurred in another pair of galaxies, anywhere within about 3.25 million light-years of us, gravitational wave detector technology comparable to what we have now could detect it, assuming the detectors are designed to observe at the right frequencies. The merger of supermassive black holes produces gravitational waves at lower frequencies than the stellar mass black hole mergers that LIGO has detected. LIGO is sensitive to frequencies of roughly 10 to 1000 Hertz, appropriate for black holes, weighing tens of solar masses. Supermassive black hole mergers produce waves at frequencies measured in microhertz to millihertz, far below LIGO's range. Detecting these waves requires different instruments. Proposed space-based detectors like LISA, the Laser Interferometer Space Antenna, would be sensitive to exactly these frequencies. LISA, if built and launched as currently planned, would be able to detect supermassive black hole mergers across cosmological distances, potentially observing dozens or hundreds of such events per year across the universe. Future gravitational wave observatories will routinely detect supermassive black hole mergers. Each detection will provide information about galaxy evolution, black hole growth, the nature of space-time in extreme gravitational fields, and tests of general relativity under conditions impossible to reproduce in any laboratory. The Milky Way Andromeda black hole merger, when it happens billions of years from now, will be an event of cosmic significance, one of the most energetic occurrences possible in the universe short of the Big Bang itself. The merged black hole will sit at the center of the merged galaxy, likely fed by gas from the disrupted galactic disks, possibly becoming an active galactic nucleus for a time, shooting jets of particles outward at nearly the speed of light, blazing across the electromagnetic spectrum. But eventually, once the available gas is consumed or blown away, it will settle down, becoming quiescent like the black holes in the Milky Way and Andromeda are today. It will wait at the galactic center, occasionally flaring when it swallows a wayward star or gas cloud, but mostly quiet, the dark heart of a New galaxy, born from the merger of two old ones. What if the collision doesn't happen? The 2025 study by Till Sawala raised a possibility that many people find surprising. What if the collision doesn't happen at all? Given all we've discussed about the inevitable merger, how could it not occur? The answer lies in the gravitational complexity of the local group and the genuine uncertainties in our measurements. Sawala's team included the Triangulum Galaxy and the Large Magellanic Cloud in their simulations, two massive objects that previous studies had often simplified or excluded. When you add these additional gravitational influences and properly account for measurement uncertainties, the range of possible futures expands dramatically. In roughly half of Sawala's simulations, the Milky Way and Andromeda made close approaches but didn't fully merge within the 10 billion year time frame modeled. This doesn't necessarily mean they'll never merge. It might just take longer, perhaps 15 or 20 billion years instead of 7 to 10 billion. Or the galaxies might exchange energy in such a way that they remain as separate, though gravitationally bound, structures indefinitely. Think of it like binary stars that orbit each other without merging. They're bound by gravity, dancing around their common center of mass, but they maintain their separate identities. Could the Milky Way and Andromeda end up in a similar configuration, orbiting each other for tens of billions of years without merging? It's possible based on the simulations, though we should emphasize this is one potential outcome among many. The gravitational interactions are complex enough that small differences in initial conditions, differences within our current measurement uncertainties, can lead to qualitatively different outcomes. This is the nature of what mathematicians call chaotic systems, where sensitivity to initial conditions makes long-term prediction fundamentally difficult. If the collision doesn't happen or happens much later than current estimates suggest, what would that mean for the local group? The Triangulum Galaxy would continue orbiting Andromeda, possibly eventually merging with it in a separate event. The Magellanic Clouds might continue orbiting the Milky Way, or might be captured by Andromeda during a close pass. Smaller dwarf galaxies would continue being gradually absorbed by the larger galaxies. The local group would remain recognizable as a cluster of distinct galaxies for much longer than in the merger scenario. Instead of collapsing into a single massive elliptical by 10 billion years from now, we'd have a more gradual evolution with multiple large galaxies coexisting. This scenario might actually be more common in the universe than we've traditionally thought, based on the Sawala study's implications. Many galaxy pairs that appear headed for collision might actually be in long-term orbital configurations that postpone or prevent merger. This would have implications for how we understand galaxy evolution across cosmic history. However, we should be clear about what the uncertainty means and doesn't mean. It doesn't mean Andromeda isn't approaching us. That's observed fact, measured repeatedly. It doesn't mean the galaxies aren't gravitationally bound. They almost certainly are. What it means is that the exact outcome, when projected billions of years forward, remains genuinely uncertain given current data. Future observations will help reduce this uncertainty. Better measurements of the Triangulum Galaxy's mass and orbit, more precise determinations of the Milky Way's total mass from Gaia data, improved measurements of Andromeda's structure and dark matter distribution. Each refinement narrows the range of possible futures. but some irreducible uncertainty will likely always remain when predicting events billions of years ahead. The system is too complex with too many interacting variables for perfect prediction. We can map out the most likely outcomes and understand the physics governing the possible futures, but we can't say with absolute certainty which future will actually unfold. This uncertainty is actually one of the beautiful things about science. It doesn't claim omniscience. It provides the best predictions possible given current evidence, always ready to update those predictions as new evidence arrives. The story of the Milky Way Andromeda collision is still being written, both by the galaxies themselves as they slowly approach, and by the scientists working to understand what will happen when they meet. When Andromeda hits the Milky Way, Part 3, The Birth of Milkdromeda. After billions of years of approaching, colliding, separating, and colliding again, after the supermassive black holes have merged and the violence of multiple encounters has played out, what emerges is something new, a single galaxy born from the merger of two spirals. Astronomers have playfully dubbed this future galaxy Milkdromeda, sometimes also called Milkdromeda, a portmanteau of Milky Way and Andromeda. Milkdromeda will almost certainly be a giant elliptical galaxy. This isn't speculation. We can observe thousands of elliptical galaxies in the universe today, and computer simulations have shown convincingly that major mergers between spiral galaxies naturally produce elliptical galaxies. The process, based on what we understand from both observations and simulations, is well established. Here's how it works. Spiral galaxies, like the Milky Way and Andromeda, are supported by ordered rotation. Stars orbit in roughly the same plane, creating a flattened disk. This ordered rotation is what creates and maintains the spiral structure through density wave patterns. But when two spirals collide, particularly if their rotation axes are not perfectly aligned, the ordered motion gets scrambled. As the galaxies merge, stars from both systems are gravitationally deflected by encounters with concentrations of mass from the other galaxy. Stars that were orbiting peacefully in the plane of the Milky Way's disk get thrown onto tilted or elliptical orbits by gravitational interactions with Andromeda's stars and dark matter. Stars from Andromeda's disk experience the same scattering from encounters with Milky Way material. Over hundreds of millions of years, billions upon billions of these gravitational interactions accumulate. The result is a population of stars on orbits with random orientations. Some stars orbit in one plane, others in perpendicular planes, still others on highly elongated elliptical orbits that take them far from the galactic center and back. The ordered rotation of a disk galaxy gets replaced by random motion, what astronomers call velocity dispersion. The stars are still orbiting the galactic center, governed by gravity just as before, but there's no longer a preferred plane or direction. Without ordered rotation to flatten it into a disk, the galaxy settles into a roughly spherical or ellipsoidal shape. This is what defines an elliptical galaxy. The shape is supported not by rotation, but by the random velocities of the stars, similar in principle to how gas pressure supports the sun's atmosphere against gravity. It's a fundamentally different structure from a spiral galaxy, maintained by different physics. Milkdromeda will be a giant among elliptical galaxies, based on what we can project from the combined masses of the two parent galaxies. It will contain between 1 trillion and 1.5 trillion stars. Nearly all the stars from both the Milky Way and Andromeda combined. Some stars will be ejected entirely during the merger, flung out at high speeds by gravitational encounters, becoming intergalactic wanderers. But simulations suggest that most stars, perhaps 80 to 90%, will remain gravitationally bound to the merged system. The size of Milkdromeda is harder to predict with precision. Elliptical galaxies don't have well-defined edges the way spiral galaxies do. They fade gradually into space, with ever-decreasing stellar density extending outward. Astronomers measure elliptical galaxies using something called the effective radius, which contains half the total light. Based on the masses and structures of the parent galaxies, Milkdromeda's effective radius will likely be somewhere around 15,000 to 20,000 light years, though this is an approximate estimate. Interestingly, this is actually smaller than the combined sizes of the Milky Way and Andromeda disks. The Milky Way spans about 100,000 light years, Andromeda about 220,000. You might expect the merged galaxy to be larger, but ellipticals are typically more compact than spirals of comparable mass. The stars get mixed together and settle into a denser configuration supported by random velocities rather than spreading out in a rotating disk. The central region of Milkdromeda will be extraordinarily dense with stars. The combined stellar populations from both galactic bulges will create a core containing hundreds of billions of stars in a relatively small volume. If you could somehow place the Sun in the central regions of this future galaxy, assuming the Sun still existed in any recognizable form, the night sky would be transformed beyond recognition. Thousands of stars would be bright enough to cast shadows. The combined starlight would create perpetual twilight, making true darkness impossible. However, simulations suggest that Milkdromeda's core might actually be less dense than typical massive elliptical galaxies formed from mergers, at least in the very center. The merger process can create what's called a core deficit. When the two supermassive black holes spiral together, they scatter nearby stars through gravitational interactions, ejecting them from the very center before the black holes finally merge. This creates a small region around the merged black hole with lower stellar density than you'd expect, based on the galaxy's overall structure. This effect has been observed in many elliptical galaxies that show evidence of past mergers. The color of Milkdromeda will likely be reddish, based on what we can infer from observations of similar merger remnants. During the merger, bursts of star formation will create lots of young blue stars, but star formation will decline rapidly after the merger completes. Most of the gas will either be consumed forming stars during the collision or heated and blown away by energy from supernova explosions and stellar winds. Without cold gas available, new stars cannot form. As the blue stars age and die over hundreds of millions of years, leaving behind only the longer-lived red and yellow stars, the galaxy's integrated color will shift redward. Within perhaps a billion years of the merger completing, Milkdromeda will appear distinctly red, dominated by the light of old stellar populations. This is typical of elliptical galaxies, which are sometimes described in the astronomical literature as red and dead because they are full of old stars with little or no ongoing star formation. But Milkdromeda won't be completely dead, at least not for a very long time. Small amounts of gas will remain or be acquired through accretion from intergalactic space, allowing star formation to continue at a very low rate. The galaxy might also consume smaller satellite galaxies over subsequent billions of years, each minor merger adding new material and potentially triggering small bursts of star formation. So there might be some young stars scattered through the population, but they'll be a tiny minority in a galaxy dominated by ancient suns. The structure of Milkdromeda will bear the marks of its violent formation, at least for billions of years. Tidal tails from the collision might persist for a very long time, long streamers of stars extending hundreds of thousands of light years into space, slowly dispersing or falling back into the main galaxy. Computer simulations and observations of merger remnants suggest these features can remain visible for billions of years before they fully phase mix and disappear. The total mass of Milkdromeda, including dark matter, will be approximately 2 to 3 trillion times the mass of the Sun, based on combining the estimated masses of both parent galaxies. The dark matter halos will merge, creating a single massive halo, extending perhaps 1 million light years or more from the galactic center. This dark matter will dominate the gravitational field of the merged galaxy, just as it dominates both the Milky Way and Andromeda today, accounting for roughly 85 to 90% of the total mass. At the heart of Milkdromeda will sit the merged supermassive black hole, weighing somewhere between 100 and 200 million solar masses. For a time, after the merger, this black hole might become very active if gas from the disrupted galactic disks falls into it. The infalling material would form an accretion disk heating to millions of degrees and emitting intense X-rays and other high-energy radiation. Jets of particles might shoot outward from near the black hole at nearly the speed of light, powered by the tremendous energy available from matter, falling into such an intense gravitational field. Milkdromeda could briefly, for perhaps tens of millions of years, become what astronomers call an active galactic nucleus, outshining the rest of the galaxy in certain wavelengths. But this active phase wouldn't last indefinitely. Once the available gas near the black hole is consumed or blown away by the energy output of the active nucleus itself, the black hole would settle down, becoming quiescent like the black holes in the Milky Way and Andromeda are in our current era. It would sit at the galactic center, occasionally flaring when it swallows a wayward star or when a gas cloud wanders too close, but mostly quiet. Milkdromeda will be one of the largest galaxies in the local group, possibly the largest if the Triangulum galaxy also merges with it at some point during or after the Milky Way-Andromeda collision. But in the scale of the universe, it will be just one of trillions of elliptical galaxies. Many of these formed through similar merger processes billions of years ago. Milkdromeda will be unique and special to any conscious beings that might exist within it, the descendant of our cosmic home. But to the universe at large, it will be unremarkable. One more galaxy among countless others. Earth and our solar system's fate. One of the most common questions people ask when they first hear about the Milky Way-Andromeda collision is deeply personal. What will happen to Earth? Will our planet be destroyed? Will our solar system survive? The answers are complex and depend very much on what you mean by survive. Let's start with the reassuring news. When galaxies collide, individual stars almost never collide with each other. We've emphasized this point before, but it bears repeating because it's so counterintuitive. The distances between stars are simply too vast. In our region of the Milky Way, The nearest star to the Sun is Proxima Centauri, at 4.2 light years away. If you were to scale the Sun down to the size of a grain of sand about 1 millimeter across, Proxima Centauri would be another grain of sand roughly 30 kilometers or 19 miles away. Even in the dense cores of galaxies where stars are packed much more closely together, the average separation is still measured in light months or light years. When two galactic disks pass through each other, the stars simply thread between each other like two swarms of gnats interpenetrating. The probability of any two stars actually physically colliding is negligible, far less than 1 in a trillion based on reasonable estimates of stellar densities and collision cross sections. So the Sun won't collide with another star during the merger. The planets won't be vaporized by a stellar impact. In that direct physical sense, the solar system will almost certainly survive the collision itself. The Earth won't be destroyed by the collision, at least not by direct impact. But survival doesn't mean things will remain unchanged. The gravitational interactions during the merger will affect the Sun's orbit around the galactic center. Right now, the Sun orbits at a distance of about 26,000 light years from the Milky Way's core, completing one orbit every 225 to 250 million years in a roughly circular path through the galactic disk. During the collision, gravitational encounters with passing stellar concentrations and interactions with the overall changing gravitational field of the merging galaxies will perturb this orbit. The Sun's path will be deflected, its distance from the galactic center will change, and it might be thrown out of the plane of the disk entirely. Simulations published in 2008 by astronomers T.J. Cox and Abraham Loeb attempted to predict what would happen to the solar system. They ran numerous simulations of the merger with different initial conditions and tracked the fate of stars in positions similar to the Sun's current location. Their results suggested that there's approximately a 50% chance the Sun will be flung outward to about 3 times its current distance from the galactic center. That would place us roughly 80,000 light years out, far from the center of Milkdromeda, in the outer halo region where stellar density is very low. There's also a smaller probability, which they estimated at about 12%, that the solar system could be ejected from the galaxy entirely. A particularly violent series of close gravitational encounters could give the Sun enough velocity to escape Milkdromeda's gravitational pull. We'd become an intergalactic wanderer, a star drifting through the void between galaxies with our planet still in tow. Neither of these outcomes would necessarily be catastrophic for the solar system itself, at least. Not from a purely mechanical standpoint. The Sun's energy comes from nuclear fusions in its core, converting hydrogen into helium through the proton-proton chain reaction. This process doesn't depend on anything happening in the galaxy around us. Whether the Sun is in the heart of a galaxy, in the outer halo, or adrift in intergalactic space, it will continue shining as long as it has hydrogen fuel to burn. If the Sun were ejected into intergalactic space, the night sky from Earth would change dramatically, though by that point we need to ask whether Earth would still exist in any recognizable form. Instead of seeing the band of the Milky Way and the bright stars of our stellar neighborhood, the sky would be profoundly dark. Milkdromeda would appear as a vast, faint structure covering a large portion of the sky, but individual stars would be invisible from our great distance. It would be perhaps the loneliest view imaginable. A single star, and its planets drifting through the cosmic void with only distant galaxies for company. But here's the crucial point that makes all these considerations about the galaxy collision somewhat academic. None of this matters for Earth's survival as a living world, because Earth will almost certainly be long gone before the collision even begins. The reason has nothing to do with the galactic merger. It has to do with the sun's own evolution, which follows a predictable path determined by the physics of stellar structure. Stars like the sun gradually increase in luminosity as they age. This happens because as hydrogen in the core is converted to helium through fusion, the helium accumulates in the core. Helium is denser than hydrogen, so the core slowly contracts under its own weight, even while fusion continues. This contraction heats the core, which causes fusion to proceed faster, which produces more energy, which makes the star brighter. The effect is gradual but inexorable. About 4 billion years ago, when the sun was newly formed, it was roughly 70% as bright as it is today. In another billion years from now, it will be about 10% brighter than it currently is. This might not sound like much, but it's enough to fundamentally and catastrophically change Earth's climate. The increased solar radiation will heat the planet. This will cause more water to evaporate from the oceans. Water vapor is a powerful greenhouse gas, so this will heat the planet further, causing more evaporation in a runaway feedback loop that climate scientists call a moist greenhouse effect. The atmosphere will become thick with water vapor. Surface temperatures will rise. Within approximately 1 billion years from now, perhaps 1.5 billion, at the outside, based on the most optimistic climate models, Earth's oceans will completely evaporate. The water will be broken apart by ultraviolet radiation in the upper atmosphere. Hydrogen, being very light, will escape to space. Oxygen will combine with rocks in the crust through oxidation reactions. Earth will become a dry, hot world with a thick atmosphere dominated by carbon dioxide and water vapor, surface temperatures reaching several hundred degrees Celsius. All life as we know it will be extinct. This happens roughly 2.5 to 3 billion years before the first close encounter with Andromeda. By the time the galaxies collide, Earth will have been a dead, desiccated world for billions of years. But the story doesn't end there. About 5 billion years from now, give or take a few 100 million years based on stellar evolution models, the sun will exhaust the hydrogen in its core. Fusion will cease in the core, which will begin to contract under its own gravity. This contraction will heat the surrounding layers, which still contain hydrogen. Fusion will ignite in a shell around the inert helium core. This shell burning produces tremendous energy, causing the sun's outer layers to expand enormously. The sun will become a red giant, swelling to perhaps 100 or even 200 times its current radius based on stellar evolution models. It will certainly engulf Mercury, and it will certainly engulf Venus. Whether it will engulf Earth is genuinely uncertain and depends on details of how much mass the sun loses as it expands and how this affects Earth's orbit. Some models suggest Earth's orbit will be pushed outward by the decreasing solar mass, keeping our planet just ahead of the expanding stellar atmosphere. Other models suggest Earth will be swallowed, spiraling inward through friction with the extended atmosphere until it's vaporized. Either way, Earth as a habitable world is finished long before this point. If the planet is engulfed, it will be destroyed, its atoms dispersed into the sun's atmosphere. If it survives by being pushed outward, It'll be a charred, lifeless cinder, orbiting close to a bloated red star, its surface glowing red-hot from the intense radiation. The red giant phase lasts for about 1 billion years. During this time, the Sun will lose approximately half its mass through stellar winds, powerful flows of particles streaming away from the star's extended atmosphere. Eventually, the core will become hot enough and dense enough to fuse helium into carbon and oxygen. This helium burning is brief and somewhat unstable, lasting only about 100 million years. When the helium is exhausted, the Sun will shed its outer layers in what astronomers call a planetary nebula. Despite the name having nothing to do with planets, it's a beautiful, expanding shell of glowing gas illuminated by ultraviolet radiation from the exposed core. What remains is that core, now revealed as a white dwarf about the size of Earth, but containing about 60% of the Sun's original mass. This white dwarf will slowly cool over trillions of years, eventually becoming a black dwarf, a cold, dark object invisible except through its gravitational influence. By the time Milkdromeda fully forms, perhaps 7 to 10 billion years from now. Based on the merger timeline estimates, the Sun will likely be a white dwarf, slowly cooling in the darkness. The planets, if any survive, will be frozen worlds orbiting a fading ember. There will be no Earth as we know it, no life, nothing recognizable from our current era. So when we ask whether Earth survives the collision with Andromeda, the answer is nuanced. The planet itself might physically survive as a ball of rock, though whether in orbit around the Sun or vaporized during the red giant phase is uncertain. The solar system will certainly survive in some form, though its location in the galaxy might change dramatically. But Earth as a living world, Earth as our home, will be gone long before Andromeda arrives. This might seem depressing, but there's a different way to look at it. If humanity or our descendants still exist in any form when the collision occurs billions of years from now, they will have achieved something truly remarkable. They will have survived for billions of years, weathering the death of their home planet, the transformation of their parent star, and countless other challenges we can barely imagine. They might have spread to other star systems, other galaxies. They might exist in forms we wouldn't recognize as human. But if consciousness born on Earth still exists somewhere when Milkdromeda forms, that consciousness will have persisted across cosmic timescales, and that would be an achievement of profound significance. Other mergers across the universe. The collision between the Milky Way and Andromeda, while momentous for us, is far from unique in the universe. Galaxy mergers are common, happening constantly on cosmic scales. We can observe thousands of galaxies in various stages of merging right now, providing previews of what our own galactic future might look like if the collision occurs. One of the most famous and well-studied examples is the antennae galaxies, officially cataloged as NGC 4038 and NGC 4039, located approximately 45 to 65 million light-years away in the constellation Corvus. These two galaxies are caught in the middle of a dramatic collision. The merger provides an invaluable window into galaxy collision physics because the antennae are close enough for detailed study, but far enough along in their merger to show dramatic features. About 1.2 billion years ago, based on reconstructions from computer simulations, the antennae were two separate, normal spiral galaxies. NGC 4038 was a barred spiral, and NGC 4039 was a regular spiral galaxy. They orbited each other peacefully for billions of years before their separation began to decrease under mutual gravitational attraction. Approximately 900 million years ago, the two galaxies began their approach toward each other, still looking relatively normal, similar to how galaxy pairs in the early stages of interaction appear in surveys today. Then, about 600 million years ago, they made their first close pass, passing through each other in their first violent encounter. During this pass, tidal forces began to pull stars out of both galaxies. The tidal tails, the long streamers of stars that give the antennae their name, formed about 200 to 300 million years ago, during and after that first encounter. When you look at images of the antennae galaxies taken by ground-based telescopes, the most striking features are these tails. They look like an insect's antennae, hence the popular name. These tails extend for hundreds of thousands of light years, composed of stars who were pulled out of both galaxies by differential gravitational forces. The cores of the two galaxies are still visible as distinct bright regions in high-resolution images, showing that despite being 600 million years into their collision, the merger is still in progress. They haven't yet combined into a single structure. Between the cores lies what astronomers call the overlap region, where the two galactic disks are interpenetrating, passing through each other. This region is full of dense dust clouds and extraordinarily active star formation. The collision has triggered an intense burst of star formation, exactly the kind of starburst we would expect during the Milky Way Andromeda collision. Normally, galaxies like the Milky Way form about one solar mass worth of new stars per year. During the peak of the collision in the antennae, star formation rates increased dramatically. The galaxies are forming stars at rates many times higher than normal spiral galaxies. The Hubble Space Telescope has observed the antennae in exquisite detail. The images, some of the most spectacular ever captured of a galaxy collision, show over 1,000 bright, compact young star clusters that have formed during the collision. These are called superstar clusters, massive concentrations, each containing tens of thousands of young stars packed into regions only a few light years across. They shine brilliantly in ultraviolet and visible light, markers of recent star formation. Most of these superstar clusters are extremely young, only a few million to tens of millions of years old, and based on studies of their properties and comparison with similar objects in other merging systems, most of them will eventually disperse. When massive stars in the clusters explode as supernovae, the energy input can unbind the cluster, causing it to gradually dissolve with stars drifting apart. Observations and modeling suggest that about 90% of the superstar clusters formed during the collision will disperse within the first 10 million years. But about 100 of the most massive clusters, based on current estimates, will survive. They're gravitationally bound tightly enough that they can withstand supernova explosions and the gradual evaporation of stars from their outer regions. These survivors will become globular clusters, similar to the ancient globular clusters that orbit the Milky Way and Andromeda today. We're watching the formation of a new generation of globular clusters in real time, cosmically speaking. The antennae galaxies show us what the Milky Way Andromeda collision might look like during its active phase, assuming the collision occurs. The long tidal tails streaming through space, the intense star formation in the overlap region, the chaotic mixing of stars from two galaxies, All of this will likely occur when our galaxies meet, based on what physical principles we understand from studying systems like the antennae. However, there's an important difference worth noting. The antennae galaxies are gas-rich spirals that still had substantial reserves of star-forming material when they collided. There was lots of cold molecular gas available to be compressed and shocked into forming new stars. The Milky Way and Andromeda, 4 billion years from now, will have much less gas available, based on current star formation rates, and the time available to convert gas into stars. They'll have used up most of their gas, forming stars over the intervening billions of years. This suggests, though we should note this is an inference rather than a certainty, that the starburst during our collision might be less intense than what we observe in the antennae. There will still be enhanced star formation where gas clouds collide, but it might be more subdued. Some studies have suggested the merger might be relatively gas-poor, with insufficient gas remaining to fuel a dramatic starburst. If that's the case, Milkdromeda might form relatively quietly compared to more spectacular mergers we observe at earlier cosmic epochs when galaxies were generally more gas-rich. Other observed mergers throughout the universe show different stages and outcomes. The mice galaxies, NGC 4676, show two spirals that have passed through each other and are separating, with long tidal tails trailing behind them like the tails of mice. Eventually, they'll fall back together and merge. The whirlpool galaxy M50 and its smaller companion NGC 5195 show a different scenario. A minor merger where the smaller galaxy is passing by the larger one, dramatically enhancing the spiral structure of M51 through tidal interactions. NGC 520 shows what appears to be a merger in an advanced stage. The two original galaxies have already combined into a single structure, but the system is still settling down. It appears chaotic and asymmetric in images, with twisted dust lanes and multiple concentrations of stars. Over billions more years, it will likely relax into a more regular elliptical galaxy. By studying these systems and hundreds of others in various stages of merger, astronomers can test their computer simulations and understand the physics of galaxy collisions. The simulations can be compared with real observations. When they match, we gain confidence that we understand the processes involved. When they don't match, we learn something new about galaxy physics and can refine our models. The antennae are particularly valuable for this purpose. They're close enough that Hubble can resolve individual star clusters, allowing detailed study of star formation during mergers. They're at a stage of the merger where activity is intense, showing what happens during the peak collision phase. And they've been studied across the electromagnetic spectrum, from radio waves through visible light to X-rays, providing a comprehensive picture. Observations of the antennae have taught us that galaxy collisions compress gas clouds, triggering star formation. They've shown us that most newly formed clusters disperse quickly, while a minority survive to become globular clusters. They've revealed that supernovae from short-lived massive stars inject enormous energy into the interstellar medium, creating bubbles and shells of hot gas. All of these processes will likely occur during the Milky Way Andromeda collision if it happens. These colliding galaxy systems, scattered throughout the universe, provide windows into our potential future. They allow us to see what might happen when our own galaxies meet, based not on pure speculation, but on physical processes we can observe occurring elsewhere in the cosmos, the far future, beyond the merger. After Milkdromeda forms, after the merger is complete, and the new galaxy has settled into a stable elliptical configuration, what happens next? The story doesn't end with the formation of the merged galaxy. Milkdromeda will continue to evolve over timescales that dwarf even the merger timeline itself. For the first billion years or so after the merger completes, Milkdromeda will still show signs of its violent formation. Residual star formation will continue in regions where gas was compressed during the collision. Tidal streams and shells from the merger will persist in the outer halo, gradually fading as the stars within them disperse. The central supermassive black hole might be active, fed by gas from the disrupted disks. But over time, these signatures will fade. Star formation will decline as the available gas is exhausted or blown away by energy from supernovae and stellar winds. The tidal features will phase mix and disappear. The black hole will consume its supply of nearby gas and become quiescent. Within a few billion years, Milkdromeda will have settled into a stable configuration, a giant elliptical galaxy showing few obvious signs of its merger origin. Star formation will continue at a very low rate for a long time. Even after most of the gas is gone, small amounts will accrete from intergalactic space or be recycled from dying stars. Red giants shed their outer layers, and planetary nebulae return material to the interstellar medium. This gas can cool and potentially form new stars, though at a much slower rate than during Milkdromeda's early history. But the overall trend is clear and inevitable. Milkdromeda will slowly convert its remaining gas into stars, and eventually the gas will run out. Star formation will cease. At that point, Milkdromeda would truly be red and dead, an elliptical galaxy with no new stars being born, gradually aging as its stellar population evolves. The stars themselves will age and die on various timescales. Massive stars will be gone first, having already exploded as supernovae within just a few million to tens of millions of years of forming. Medium-mass stars like the Sun live for billions of years before evolving into red giants and eventually white dwarfs. Small red dwarf stars can live for trillions of years, far longer than the current age of the universe. Over time, measured in trillions of years, all the stars capable of fusion will exhaust their fuel. What remains will be stellar remnants, white dwarfs from low and medium mass stars, neutron stars, and black holes from massive stars, and perhaps a few of the smallest red dwarfs still fusing hydrogen. Milkdromeda will become a galaxy of fading embers and dead cinders, with only the smallest, longest-lived stars still shining, but even those will eventually die. Over tens of trillions of years, the last red dwarfs will slowly exhaust their hydrogen and fade, becoming brown dwarfs and then black dwarfs as they cool. Eventually, perhaps 100 trillion years from now, Milkdromeda will contain no living stars. It will be a ghost galaxy, full of stellar remnants, all invisible except through their gravitational influence. Meanwhile, something else will be happening on even larger scales. The universe is expanding, and observations indicate that expansion is accelerating, driven by what we call dark energy. Distant galaxies are moving away from us, faster and faster. Currently, we can see thousands of galaxies with our telescopes scattered across billions of light years. But as the expansion continues, more and more galaxies will recede beyond the cosmic horizon, the distance beyond which Light can never reach us, no matter how long we wait. In a few trillion years, based on cosmological models, all the galaxies outside the local group will be too far away to see. Their light will be redshifted to invisibility, stretched by the expanding space between us until it becomes undetectable. An observer in Milkdromeda at that time, looking out into space, would see only the members of the local group, the galaxies, gravitationally bound to each other and immune to the cosmic expansion. And even the local group will continue evolving. Smaller galaxies will merge with Milkdromeda. The Triangulum galaxy, if it hasn't already merged, will eventually be consumed. Dwarf galaxies will be slowly torn apart by tidal forces and absorbed. Over perhaps 100 billion years or more, Milkdromeda will cannibalize the entire local group. By 100 trillion years from now, Milkdromeda will probably be the only galaxy visible in what remains of the observable universe. Everything else will have expanded beyond the cosmic horizon. An observer in this far future would see a universe containing just their galaxy, surrounded by empty space extending to infinity. It would be profoundly lonely, the ultimate cosmic isolation. But even Milkdromeda itself won't last forever in its current form. Over timescales of quadrillions of years, even gravitationally bound systems slowly evaporate through a process that's somewhat random but statistically inevitable. Stars occasionally have close encounters with each other. Most encounters simply exchange orbital energy, leaving both stars still bound to the galaxy. But occasionally, a star gains enough energy to escape the galaxy's gravitational pull entirely. These ejections happen rarely for any individual star, but given enough time, they accumulate. Over quadrillions of years, the galaxy slowly disperses, stars escaping one by one into the void. What's left becomes more concentrated, denser as the loosely bound outer regions evaporate away. This is the ultimate fate of Milkdromeda and all galaxies, based on our current understanding. Slow dissolution over timescales, almost impossible to comprehend, scattered into the ever-expanding darkness of a dying universe. But that's a story for a time so far in the future it's almost meaningless to contemplate. For now, we can focus on the nearer future, the next 10 billion years or so, when the collision with Andromeda might occur and Milkdromeda might be born. Conclusion and cosmic perspective. We've journeyed through billions of years tonight, from our present moment watching Andromeda as a faint smudge in the night sky, to a potential future when our galaxy and Andromeda merge into a single new structure. We've explored the timeline of the collision, watched as two massive spiral galaxies approach and interpenetrate multiple times over billions of years. We've witnessed the merger of supermassive black holes in a cataclysmic release of gravitational wave energy. We've seen the birth of Milkdromeda, a giant elliptical galaxy that might emerge from the merger. We've confronted the sobering reality that Earth, as a living world, will be long gone before any of this occurs, victim not of the galactic collision, but of our own sun's inevitable evolution. We've looked at other colliding galaxies throughout the universe, seeing in systems like the antennae a preview of what might happen when our own galaxies meet. We've examined the science behind these predictions, the computer simulations and careful observations that allow us to glimpse the future despite the enormous uncertainties involved. And we've peered even farther forward into a future so distant it challenges comprehension, when Milkdromeda itself will fade and disperse into the expanding darkness. But what does all this mean? Why should we care about something that won't happen for billions of years, long after everything we know has vanished? There are several reasons, and they touch on some of the deepest questions about our existence and our place in the cosmos. First, understanding galaxy. Collisions helps us understand how galaxies form and evolve. The Milky Way itself formed partly through mergers with smaller galaxies billions of years ago. We can see evidence of these ancient collisions in stellar streams and chemical signatures in our galaxy's halo. Andromeda shows signs of past mergers in its disturbed stellar populations. What will happen in the future has happened countless times in the past. By studying galaxy mergers, we learn about the processes that created the structures we see around us today. Second, it puts our existence in profound perspective. We live on a small planet orbiting an average star in a galaxy containing hundreds of billions of stars. That galaxy is just one of trillions in the observable universe. And all of it, all the vast structures we can see, are temporary on cosmic timescales. Galaxies collide and merge. Stars are born and die. Even the galaxies themselves will eventually dissolve. Yet here we are, conscious beings, capable of understanding this grand cosmic story. We can look up at Andromeda, measure its motion, predict its future, and envision what will happen billions of years from now. We can run simulations on computers and observe colliding galaxies across billions of light years and piece together a coherent picture of galaxy evolution. That's extraordinary. We're temporary patterns in the flow of energy and matter through space-time, but we're patterns complex enough to understand the larger patterns we're part of. Third, it reminds us of the vast timescales of the cosmos compared to human experience. All of recorded human history spans perhaps 6,000 years. Our species has existed for 300,000 years. The collision will occur 4 billion years from now, more than 10,000 times longer than all of human history. The merger will take another 3 to 6 billion years to complete. On these timescales, nothing we worry about, nothing we consider important in our daily lives, has any cosmic significance. Nations rise and fall. Species evolve and go extinct. Continents drift. Stars are born and die. Galaxies merge. The universe operates on scales that dwarf human concerns. But that's not depressing. It's liberating. We don't need cosmic permanence to justify our existence or find meaning in our lives. We exist now in this brief moment between deep past and deep future. What we do for ourselves, for each other, for the things and people we care about in the present. The universe doesn't care about us, but that doesn't mean we can't care about each other and find meaning and beauty and purpose in our brief time here. And there's something profound about being part of this vast cosmic story. The atoms in your body were forged in the cores of stars that exploded billions of years ago, scattering their enriched material through space. Those atoms cycled through gas clouds, through previous generations of stars, through planets, through countless forms, before finally assembling into you. You're made of stardust, literally. And someday those atoms will return to space, perhaps incorporated into future stars, or planets, or beings we can't imagine, continuing the cycle. The collision between the Milky Way and Andromeda is part of that ongoing story. Galaxies form from collapsing clouds in the early universe. They grow by accreting material and merging with neighbors. They evolve over billions of years. Eventually, they merge with other galaxies or disperse into the expanding cosmos. It's a cycle of transformation, of structure forming and dissolving, and forming again, playing out over timescales that dwarf human comprehension. We're privileged to live in an era when we can understand this story. A century ago, we didn't even know other galaxies existed. Now we can observe billions of galaxies, measure their properties, predict their futures. We've learned to read the cosmic story written in starlight across billions of light years. That's an achievement worth celebrating. So when you look up at the night sky tonight and see that faint smudge in the constellation Andromeda, remember what you're seeing. You're looking 2.5 million years into the past, watching photons that began their journey before modern humans evolved. You're seeing a galaxy approaching us, slowly, inexorably, on a path that might eventually bring it into collision with our home galaxy. You're seeing a possible future written in the present. And remember that whether or not the collision occurs, whether it happens in 4 billion years or never, we're part of this vast, ancient, evolving cosmos. We're connected to everything from the smallest quantum fluctuation to the largest galactic supercluster. We're the universe made conscious, able to contemplate its own existence and evolution. The Milky Way and Andromeda are dancing through space, bound by gravity, potentially destined to merge billions of years from now. It's just one small chapter in the vast cosmic story, but it's our chapter involving our galaxy. Understanding it helps us understand our place in the universe, our connection to the larger cosmic web, and the temporary nature of everything we see. Thanks for joining me on this journey through deep time and space. If you found this exploration meaningful, please consider liking and subscribing to help the channel grow. Sleep well tonight, knowing you share this cosmos with structures so vast, processes so slow, and timescales so long that they challenge everything we think we understand about permanence and change. The universe is unimaginably large, incomprehensibly old, and profoundly dynamic. And somehow, against all odds, we're here to witness it and understand it, at least for this brief moment in cosmic time. Good night. The science of prediction. How we know what we know. How do we actually know what will happen when the Milky Way and Andromeda collide? We can't wait billions of years to observe it. We can't run experiments on real galaxies. Instead, astronomers use computer simulations, powerful mathematical models that predict the behavior of millions or even billions of particles under gravity. These simulations are called n-body simulations, where n represents the number of particles being modeled. In the context of galaxy collisions, each particle typically represents a cluster of stars, a parcel of gas, or a chunk of dark matter. The simulation calculates the gravitational force between all particles and uses those forces to determine how the particles move over time. The basic physics is straightforward, at least in principle. Newton's law of universal gravitation states that every particle attracts every other particle with a force proportional to their masses and inversely proportional to the square of the distance between them. For just two particles, calculating the force and resulting motion is trivial, something you can do with paper and pencil. For three particles, it becomes much more complicated. For millions or billions of particles, direct calculation becomes computationally impossible. This is where clever algorithms come in. The most common approach for galaxy simulations is called the Barnes-Hut algorithm, developed in 1986. Instead of calculating the force between every pair of particles, which would require n-squared calculations at each time step, The algorithm groups distant particles together and treats each group as a single object at the group's center of mass. Think of it this way. If you're calculating the gravitational force that Andromeda exerts on a single star in the Milky Way, you don't need to add up the force from each of Andromeda's trillion stars individually. You can treat the entire galaxy as a single massive object at its center of mass, at least as a first approximation. The Barnes-Hut algorithm formalizes this idea, automatically deciding when to group particles and when to calculate individual forces, reducing computational complexity from n squared to n log n. Modern simulation of galaxy collisions use millions of particles. Each particle might represent a million or even a billion solar masses of material. The simulations follow these particles forward in time, calculating gravitational forces and updating positions and velocities at each time step. Time steps are typically a few million years, small enough to capture the dynamics accurately, but large enough that the simulation doesn't take forever to run. But simulations need to model more than just gravity. They need to account for gas dynamics, because gas behaves differently from collisionless particles like stars or dark matter. When gas clouds collide, they don't pass through each other. They compress, heat up, and create shock waves. Simulations use hydrodynamic codes to model this behavior, treating gas as a fluid that can be compressed, heated, and cooled. They also need to model stellar evolution and feedback. Stars are born from collapsing gas clouds. Massive stars explode as supernovae, injecting enormous energy into the surrounding gas and potentially suppressing further star formation by heating the gas and making it harder to collapse. Including these effects is crucial for realistic predictions of how galaxies evolve during mergers. The simulations also include dark matter, which makes up most of each galaxy's mass. Dark matter particles interact only through gravity, making them simpler to model than gas, but their distribution determines the overall gravitational field that governs the merger. When galaxies collide, the dark matter halos interact gravitationally, merging over billions of years. This affects the trajectories of the visible galaxies embedded within them. Running these simulations requires enormous computational power. A detailed simulation of a galaxy merger might take weeks or months to complete even on powerful supercomputers. The simulation produces massive amounts of data, terabytes of information representing snapshots of particle positions and velocities at each time step. Researchers then analyze this data, creating visualizations and extracting quantitative predictions that can be compared with observations. The Schiavi team's 2020 simulations of the Milky Way Andromeda collision used exactly these techniques. They included both galaxies with realistic masses and structures, modeled their dark matter halos, and accounted for the diffuse gas between the galaxies. They ran many simulations with slightly different initial conditions to explore the range of possible outcomes. Their results showed the first close encounter occurring in approximately 4.3 billion years, with the full merger taking about 10 billion years to complete. They tracked the supermassive black holes through the merger process and calculated they would coalesce about 16.6 million years after the galaxies merged. They even calculated the gravitational wave output from the black hole merger, predicting it would be detectable by future gravitational wave observatories. Other research teams have run similar simulations with somewhat different results. NASA visualizations based on Hubble data suggest the first encounter at 3.75 billion years. Harvard Smithsonian Center for Astrophysics simulations give timelines of 4 to 5 billion years. These variations reflect genuine differences in approach, different assumptions about masses and dark matter distributions, different levels of detail in the modeling. The variations aren't contradictions. They represent the genuine uncertainty inherent in projecting billions of years forward from current data. We don't know the exact mass of either galaxy with perfect precision. We don't know the exact distribution of dark matter in their halos. Small variations in these parameters can shift the timeline by hundreds of millions or even billions of years, but the overall picture remains consistent across studies. If the collision occurs, it will begin in 3 to 5 billion years, proceed through multiple encounters, and result in the formation of a giant elliptical galaxy over the subsequent 3 to 7 billion years. The details vary, but the big picture is robust. How confident should we be in these predictions? The answer is nuanced. We're very confident in the basic physics. Gravity works the same way everywhere in the universe, and we understand it extremely well. We're confident in the computational methods because we can test them against galaxy collisions we observe happening elsewhere in the universe. When simulations of systems similar to the antennae galaxies reproduce the observed structures, tidal tails, and star formation patterns that gives us confidence, the simulations capture the relevant physics. When different codes developed by different teams give similar results, that's another sign we're on the right track. Where uncertainty creeps in is in the specific initial conditions and parameters. What exactly is the Milky Way's mass? What's the three-dimensional structure of Andromeda's dark matter halo? How much gas will remain in both galaxies 4 billion years from now? These are harder to pin down precisely, and variations in these parameters propagate through the simulations to create a range of possible outcomes. The 2025 study by Sawala quantified this uncertainty using Monte Carlo methods. They ran thousands of simulations with parameters randomly chosen from within observational uncertainties. About 50% showed a full merger within 10 billion years. The other 50% showed close encounters without merger or merger on longer timescales. This approach is valuable because it tells us not just what might happen, but how confident we can be. It identifies which measurements we need to improve to narrow the uncertainty. For instance, better measurements of the Triangulum galaxy's velocity and mass would significantly improve predictions based on the sensitivity analysis from the Sawala study. Future observations will help. Gaia is measuring positions and motions of billions of stars in the Milky Way with unprecedented precision, helping determine our galaxy's mass and structure more accurately. Improved radio telescope observations of neutral hydrogen in Andromeda will better map its gas distribution and dark matter. New estimates of the Milky Way's total mass from stellar kinematics continue to refine our understanding. As the data improves, the simulations will become more accurate and the range of possible futures will narrow. But there will always be some irreducible uncertainty when predicting events billions of years ahead. The system is too complex, involving too many interacting objects for perfect prediction. That's actually one of the beautiful aspects of this science. It doesn't claim absolute certainty. It provides the best predictions possible, given current evidence, quantifies the uncertainties honestly, and remains ready to update those predictions as new evidence arrives. The story of the Milky Way Andromeda collision is still being written, both by the galaxies themselves as they slowly approach, and by the scientists working to understand what will happen when they meet. Looking up, what future skies might hold. Let's take a moment to imagine what someone on Earth might see if they could somehow witness the collision. Though, as we've discussed, Earth as a habitable world will be long gone by then. But if consciousness evolved elsewhere in the solar system, perhaps on a moon of Jupiter or Saturn, after the sun became a red giant and warmed the outer solar system, what might they see? Currently, Andromeda appears as a faint, fuzzy patch in the night sky, barely visible to the naked eye under the darkest conditions. With binoculars or a small telescope, you can make out its oval shape, perhaps detect the brighter central bulge. From truly dark locations, the galaxy spans about 6 times the width of the full moon, though most of that extended structure is too faint to see without long photographic exposures. As Andromeda approaches over billions of years, it would gradually grow larger in the sky. About 1 billion years before the first encounter, it would span several degrees, far larger than its current appearance, though still relatively faint, because its light is spread over a larger area. The spiral structure might become visible to the naked eye under dark skies, 2 graceful arms winding outward from a bright central bulge. Individual bright regions in Andromeda would become visible as distinct points of light. Giant star-forming regions, each containing millions of young hot stars, would shine like bright stars in their own right. The brightest star clusters would be individually detectable. The galaxy would no longer be just a fuzzy patch, but a structured object with visible detail. By a few 100 million years before the encounter, Andromeda would dominate a large portion of the sky, spanning tens of degrees. The view would be spectacular. The spiral arms would be obvious, great sweeping curves of stars and nebulae. Bright blue regions would mark active star formation. Pink and red emission nebulae would glow where ultraviolet radiation from hot stars ionizes surrounding hydrogen gas. During the first close approach itself, the sky would be transformed. Both galaxies would fill vast portions of the celestial sphere. The spiral structures would be warped and distorted by tidal forces. Long streamers of stars would arch across the sky, tidal tails pulled from both galaxies by gravitational interactions. If star formation intensifies during the collision, as simulations and observations of other mergers suggest it might, brilliant blue regions would mark the sites of newly formed stars. These regions would be extraordinarily bright, each one comparable to many millions of suns. Supernova explosions would flash across the merged structure every few years, each one briefly outshining billions of normal stars. The night sky would never be truly dark. Even at midnight, far from any artificial lights, the combined glow of billions of stars from both galaxies would create a perpetual twilight. Traditional constellations would be unrecognizable, drowned in the overwhelming brightness of 2 galaxies' worth of stars spread across the sky. Between the close encounters, during the periods when the galaxies separate before falling back together, the view would be even more chaotic. 2 great clouds of stars would hang in the sky, connected by bridges and streams of stars stretching across hundreds of thousands of light years. Some stars would be scattered into orbits that bring them close to the sun, perhaps close enough to appear as brilliant points rivaling Venus in brightness. By the time the merger completed and Milkdromeda formed, the night sky would be uniformly filled with stars in all directions rather than showing the concentrated band of the Milky Way we see today. There would be no galactic plane, no preferred direction. Stars would surround the observer in a roughly spherical distribution characteristic of elliptical galaxies. The view would be beautiful in its own way, though profoundly different from what we see today. Instead of the Milky Way's graceful arc, we'd see stars scattered across the entire celestial sphere, brighter toward the galactic center, fading gradually toward the outskirts. On particularly clear nights, distant galaxies beyond the local group might still be visible, though by this time, billions of years from now, the universe's expansion will have carried most galaxies beyond visibility. Of course, all of this is speculation about what hypothetical observers might see. The reality is that Earth will be gone, the sun will be a white dwarf, and no human or human descendant will witness these events from our solar system. But thinking about what the sky might look like helps us visualize the scale and drama of what we're discussing, makes it more concrete and real than just abstract numbers and timescales. The collision, if it happens, will be one of the most spectacular cosmic events imaginable. A slow-motion dance of two massive spiral galaxies over billions of years, visible across millions of light years, reshaping our entire cosmic neighborhood. And somewhere, perhaps, conscious beings will watch it unfold, understanding what they're seeing, marveling at the majesty of it all. Conclusion and cosmic perspective. We've journeyed through billions of years tonight, from our present moment watching Andromeda as a faint smudge in the night sky, to a potential future when our galaxy and Andromeda merge into a single new structure. We've explored the timeline of the collision, watched as two massive spiral galaxies approach and interpenetrate multiple times over billions of years. We've witnessed the merger of supermassive black holes in a cataclysmic release of gravitational wave energy. We've seen the birth of Milkdromeda, a giant elliptical galaxy that might emerge from the merger. We've confronted the sobering reality that Earth, as a living world, will be long gone before any of this occurs, victim not of the galactic collision, but of our own sun's inevitable evolution. We've looked at other colliding galaxies throughout the universe, seeing in systems like the antennae a preview of what might happen when our own galaxies meet. We've examined the science behind these predictions, the computer simulations and careful observations that allow us to glimpse the future despite the enormous uncertainties involved. And we've peered even farther forward, into a future so distant it challenges comprehension, when Milkdromeda itself will fade and disperse into the expanding darkness. But what does all this mean? Why should we care about something that won't happen for billions of years, long after everything we know has vanished? There are several reasons, and they touch on some of the deepest questions about our existence and our place in the cosmos. First, understanding galaxy collisions helps us understand how galaxies form and evolve. The Milky Way itself formed partly through mergers with smaller galaxies billions of years ago. We can see evidence of these ancient collisions in stellar streams and chemical signatures in our galaxy's halo. Andromeda shows signs of past mergers in its disturbed stellar populations. What will happen in the future has happened countless times in the past. By studying galaxy mergers, we learn about the processes that created the structures we see around us today. Second, it puts our existence in profound perspective. We live on a small planet orbiting an average star in a galaxy containing hundreds of billions of stars. That galaxy is just one of trillions in the observable universe. And all of it, all the vast structures we can see, are temporary on cosmic timescales. Galaxies collide and merge. Stars are born and die. Even the galaxies themselves will eventually dissolve. Yet here we are, conscious beings, capable of understanding this grand cosmic story. We can look up at Andromeda, measure its motion, predict its future, and envision what will happen billions of years from now. We can run simulations on computers and observe colliding galaxies across billions of light years and piece together a coherent picture of galaxy evolution. That's extraordinary. We're temporary patterns in the flow of energy and matter through space-time, but we're patterns complex enough to understand the larger patterns we're part of. Third, it reminds us of the vast timescales of the cosmos compared to human experience. All of recorded human history spans perhaps 6,000 years. Our species has existed for 300,000 years. The collision will occur 4 billion years from now, more than 10,000 times longer than all of human history. The merger will take another 3 to 6 billion years to complete. On these timescales, nothing we worry about, nothing we consider important in our daily lives has any cosmic significance. Nations rise and fall. Species evolve and go extinct. Continents drift. Stars are born and die. Galaxies merge. The universe operates on scales that dwarf human concerns. But that's not depressing, it's liberating. We don't need cosmic permanence to justify our existence or find meaning in our lives. We exist now, in this brief moment between deep past and deep future. What we do for ourselves, for each other, for the things and people we care about in the present. The universe doesn't care about us, but that doesn't mean we can't care about each other and find meaning and beauty and purpose in our brief time here. And there's something profound about being part of this vast cosmic story. The atoms in your body were forged in the cores of stars that exploded billions of years ago, scattering their enriched material. Through space, those atoms cycled through gas clouds, through previous generations of stars, through planets, through countless forms, before finally assembling into you. You're made of stardust, literally, and someday those atoms will return to space, perhaps incorporated into future stars or planets or beings we can't imagine, continuing the cycle. The collision between the Milky Way and Andromeda is part of that ongoing story. Galaxies form from collapsing clouds in the early universe. They grow by accreting material and merging with neighbors. They evolve over billions of years. Eventually, they merge with other galaxies or disperse into the expanding cosmos. It's a cycle of transformation, of structure forming and dissolving and forming again, playing out over timescales that dwarf human comprehension. We're privileged to live in an era when we can understand this story. A century ago, we didn't even know other galaxies existed. Now we can observe billions of galaxies, measure their properties, predict their futures. We've learned to read the cosmic story written in starlight across billions of light years. That's an achievement worth celebrating. So when you look up at the night sky tonight and see that faint smudge in the constellation Andromeda, remember what you're seeing. You're looking 2.5 million years into the past, watching photons that began their journey before modern humans evolved. You're seeing a galaxy approaching us, slowly, inexorably, on a path that might eventually bring it into collision with our home galaxy. You're seeing a possible future written in the present. And remember that whether or not the collision occurs, whether it happens in 4 billion years or never, we're part of this vast, ancient, evolving cosmos. We're connected to everything from the smallest quantum fluctuation to the largest galactic supercluster. We're the universe made conscious, able to contemplate its own existence and evolution. The Milky Way and Andromeda are dancing through space, bound by gravity, potentially destined to merge billions of years from now. It's just one small chapter in the vast cosmic story, but it's our chapter involving our galaxy. Understanding it helps us understand our place in the universe, our connection to the larger cosmic web, and the temporary nature of everything we see. Thanks for joining me on this journey through deep time and space. If you found this exploration meaningful, please consider liking and subscribing to help the channel grow. Sleep well tonight, knowing you share this cosmos with structures so vast, processes so slow, and timescales so long that they challenge everything we think we understand about permanence and change. The universe is unimaginably large, incomprehensibly old, and profoundly dynamic. And somehow, against all odds, we're here to witness it and understand it, at least for this brief moment in cosmic time. Good night.